Good afternoon, and welcome at the Czech Space Week 2022 event here at Planetarium Brno. My name is Teresa Pulterová. I am a senior writer at space.com, the US headquartered publication covering all things space, and I will be your host this afternoon. And what a great timing, right? What a great timing for an event like this. 2 weeks ago, after all those hurricanes and fuel leaks, NASA's Space Launch System rocket finally lifted off from the Kennedy Space Center in Florida and sent the uncrewed Orion spaceship on the Artemis 1 mission to the moon. As you all surely know, the mission is the first step in NASA's plans to return humans on the surface of the moon by the end of this decade. Powering Orion, as you all surely know as well, is the European service module, which wasn't built in the US. It was built in Germany by Airbus in Bremen. And it wasn't only Airbus in Germany in Bremen who put this marvelous piece of technology together. Dozens of companies from all over Europe contributed components and subsystems to the mission. We can say that the European service module is a bit of a symbol of this inclusive and international era of space exploration that we currently live in. And thanks to the Czech Republic's membership in the European Space Agency, many of you sitting here today could be part of this great human endeavor, designing science experiments, building technology, and all sorts of things. And there is obviously much more. Last week, the European Space Agency announced 5 new astronauts, 1 para-astronaut, and 11 reserve astronauts. And among these 11 reserve astronauts is Czech fighter pilot Aleš Svoboda, who I believe has quite some ties to Brno. Obviously, all this is just the surface. There is so much more going on in space. There is so much to be excited about, and there is so much to discuss. And that's exactly what we're going to do in the next 5 hours. We have a really packed program. We have some really interesting speakers. For example, we will hear from a European Space Agency scientist who was part of the astronaut selection process. So perhaps she might tell us why Aleš Svoboda didn't make the final 5. We will also hear from an Austrian space architect who led an early design study of the iHub, the International Habitation Module, which will be a key part of the Lunar Gateway, the space station that NASA and its partners plan to put into the orbit around the moon within the next 5 years. And we also have a wide range of Czech scientists and experts covering fields including astronomy, astrophysics, space physiology, aerospace engineering, and many others. So it will be a very packed program. There will be 2 coffee breaks. That's important. The first at 3:50 and the second at 5:25. We will wrap up the official part of the program at 7 p.m., but an informal cocktail reception will follow, so make sure to stay around. Now, just on a side note, because we still have this COVID pandemic going on, and apparently the numbers of infections have been rising. So please, if you're not feeling very well, try to be considerate to others and consider whether you have to be here. The auditorium is not totally packed, so you can also keep some social distance. And now, without further ado, I would like to invite our first 4 speakers who will have about 3 minutes each to present their opening remarks. They are Mr. Ladislav Janíček, Director of the Brno University of Technology. Then we have Ms. Markéta Vaňková, the Mayor of the City of Brno. Hello. We also have Mr. Tomáš Kašparovský, the Dean of the Faculty of Sciences of the Masaryk University in Brno. And finally, we have Mr. Václav Kobera, who is the Director of Intelligent Transport Systems, Space Activities and Research and Development and Innovation at the Czech Ministry of Transport. He is also the head of the Czech delegation to the European Space Agency. Hello, and thank you all for joining us. And I will now ask Mr. Janíček, who is one of the main forces behind this event, to just please come first. Thank you very much.
Thank you very much for the microphone. Welcome here at this event. Welcome on behalf of the Brno University of Technology, which is the organizer of this event. And I'm very happy that you accepted this invitation to come for this event, which is organized under the auspices of the Minister of European Affairs as an event which belongs to the events organized during the Czech presidency, and also under the auspices of the Association of Research Universities of the Czech Republic. First of all, when we thought about organization of this event, we discussed that we should find some moment how we could demonstrate what we do in our universities and offer our potential to the industry. So I'm very happy that I can welcome here also representatives of the industry, which is in some way linked with space industry. To say a couple of words, I'm very happy that our Faculty of Mechanical Engineering and the Dean, Jiří Hlinka, took responsibility for the organization of this event. Our Dean of the Faculty of Electrical Engineering, Vladimír Obrecht, participated as a key partner in the organization of the event. I'm also very happy that the invitation was invited by representatives of our 5 research universities as partners who will have opportunity to give some short presentation about their education and research program. Hopefully we will have an opportunity to hear what we do, to talk and to have some discussion about not only about what we do but also about policies. So I'm very happy that invitation was invited also by the mayor of Brno, and I would also like to say that Jiří Dušek, a director of this planetarium, is unfortunately apologizing, and I would like to give him many thanks for hosting this event. He's a member of the Senate, and unfortunately he has a meeting of the Senate, so cannot be part of this event. So welcome here, and enjoy the day with round table. Thank you.
Ladies and gentlemen, Brno presents itself as a city of science, research and innovation. Hence, I am very much glad that we are gathered today on this occasion. Several companies focused on space industry are residing in our city. In the long term, we are supporting such activities and putting emphasis on education. Even foreign companies are noticing and starting to found subsidiary companies here. I believe that the Space Week Brno event will support this trend even more. A lot of smart people with fresh ideas will meet here. Many interesting ideas will be presented, and I believe that every participant will leave the event enriched. I wish you to gain as much knowledge and inspiration as possible. Science makes everyone's lives easier, and every future discovery you make can be very important. I wish you all a pleasant experience in our Brno.
Persky to follow, please.
Dear colleagues, ladies and gentlemen, it's my great pleasure to greet you on behalf of the Faculty of Science of Masaryk University, an institution closely linked to the study of the universe. More precisely, with the study and research of space. The proof is not only the participation in the today's program or activities in the neighboring observatory that serves our scientists and students. The Faculty of Science has long and systematically devoted itself to educating future astronomers and other specialists without whom we would like to impossible to move space research forward. Our scientists, academics and students make a vital contribution to exploration of the universe. We have, for example, pioneered the development of so-called small satellites with gamma-ray burst detectors, which regularly provide new and novel findings. The importance of the success of these nanosatellites is not only in the data obtained. The two projects are in prime example of collaboration between research institutions and the commercial sectors in which the students have been actively involved from the start. At the same time, they show that the space research can be carried out with budgets much smaller than certain institutions and countries can be afforded and far beyond our means. Another ambition projects, the Quick Ultraviolet Kilowatt Survey project construct of first Czech space telescope optimized for the ultraviolet part of the spectrum, which we'll discuss here, is confirmed of the effectiveness of the approach which combines the proverbial golden Czech hands with the creativity of the Czech and Slovak brains and the ability to cooperate in the international level. At the beginning of my presentation, I mentioned education. To pass on knowledge of the universe to be broader public and educate future generations, in this respect, we must do so first and foremost through teachers in primary and secondary schools. Our faculty is responsible for educating future teachers in space-related subjects, therefore this task is also our priority. We need to add another priority in the education one. Thanks to the development of satellites, we now have an enormous amount of the data about the universe, our planet, pollution, and other important changes. Therefore, we need to educate more specialists who know how to work with this data and interpret it correctly. The Faculty of Science has already signed up for this task and working a new career-oriented master's degrees program. With that I wish us all, our planet and the whole universe, every success in developing and disseminating knowledge about the universe. Thank you very much.
Thank you. And last but not least, Mr. Václav Kobera. Thank you.
Thank you very much and good afternoon to everyone. Thank you for inviting me to Brno. I'm very happy to be here. Again, I go here quite often because, well, Brno is the center of space activities in the Czech Republic. Honestly, I'm very happy to see a lot of companies here. I see a lot of academia institutes very active in space activities with this program to be newly established. I'm very happy that it's here because, well, we see that the South Moravian Innovation Center is very active. We see that the ESABIC Business Incubation Center, which was opened here in Brno too, is very active. Space in the Czech Republic has a big tradition. But over many years, it was mainly science research. And well, it's very good that we were very strong in this. After we realized that there is some business there, and well, that's why we see now quite a lot of companies involved in technologies, applications, because well, these constellations, these infrastructures which were created in the EU, like Galileo, Copernicus, they they enabled to use space for down-to-earth applications. So this is an area where we will be very strong too, where we are quite strong too. And well, you know that in the Czech Republic there is the EU Space Program Agency, which is mainly this way oriented, so it's another opportunity for us all. The Czech Republic has the presidency in EU this half a year, and I believe that we can say that we were very successful achieving the compromise on the secure connectivity. In EU there will be another infrastructure, secure connectivity mega constellation to be built soon. And this is very visible that the Czech Republic were able to achieve this success. It's also very important to say that we last week, beyond the astronaut selection, were able to increase our contributions to ESA programs because, well, the ESA is the main tool for our space program and our space endeavors because, well, there is the geographic return and the money we invest to ESA come back to our companies, to our academia. And we were able to increase, even if the economic situation is very serious, we were able to increase about 2 million euro per year. So we are now in a budget around 60+ million euro per year investing to European Space Agency. So I'm happy to be here. This is the fifth edition of the festival. We call it a festival. Of the Czech Space Week, and it's great that Brno is involved again. Thank you very much.
Thank you. Thank you all for the great opening remarks. And let's move on. So as I said, the big news last week was the announcement of the new class of European astronauts. And perhaps some of you may have been wondering why Aleš Svoboda didn't make the final 5. And perhaps our keynote speaker may be able to answer this question for us, because our keynote speaker is someone who was directly involved in the astronaut selection. Our keynote speaker is Jennifer Nguyen, who is a team leader at the Directorate of Human and Robotic Exploration at the European Space Agency. Jennifer was supposed to join us in person today, but unfortunately she contracted COVID, so she's only joining us online. Hello, Jennifer, do you hear me?
Yes, I can hear you. I hope you can hear me also.
We can hear you very well. Jennifer studied medicine at the University of Tübingen in Germany, but later she switched to neuroscience. And she obtained her PhD from Oregon Health Sciences University in Portland in the US. In 2006, Jennifer joined the European Space Agency as the young graduate trainee, and she has worked there ever since. So, Jennifer, before I give the floor to you, I just want to ask you a couple of questions. I would say it must have been a really busy 2 years for you with the astronaut selection process. Could you tell us a little bit about your involvement, your role in the astronaut selection?
Yeah, good afternoon, everybody. Thanks, Teresa, for the good question. As you just mentioned, Teresa, I'm a medical doctor and a neuroscientist by training. And within the agency, I have coordinated and overseen all science activities on board the space station. So to put it very simple, our team keeps the astronauts on board the space station busy with experiments. And during the astronaut selection process, I therefore was the science advocate, so to say, and I had to ensure that whoever is recruited to our astronaut corps understands what we're expecting from him or her and is also capable to conduct the very complex and complicated experiments on behalf of the European and international science community. Yeah, that is true. We were in a very luxurious position that allowed us to select from a huge pool of applicants. All applicants had to go through a very strict and demanding process with several steps that covered medical but also psychological aspects. Applicants also went through motivation, stress, and team building exercises. And through each of those steps, there were 7 steps in total, I believe. We narrowed down the applicant groups to 10% each time. And at the end, we were left with the lucky 16.
The final 5 from the reservists.
Well, it's actually the first time that ESA established a reserve pool of astronauts. The reason for the reserve list is that we would like to be prepared in case new, unexpected flight opportunities arise. You may know that up until now, missions to the ISS were limited to a very small circle of highly trained, super healthy people. But through advances in technology and also commercialization, space is opening up also to normal people. And we therefore need to be prepared for new opportunities. And that is why a reserve pool of astronauts has been established. So there are astronaut candidates who were successful throughout the entire selection process, but cannot yet be recruited because we have not yet identified enough flight opportunities. But as soon as a flight opportunity has been identified, also the astronaut candidates or the ones in the reserve pool will start the basic training. And until then, they remain with their current employers and help us as ambassadors to the program.
Thank you, and I will now leave the floor to you.
Thank you very much. Can you confirm that you see my slide?
We do see your slide.
Okay, perfect. So again, good afternoon to all of you. Thank you for the very nice introduction, and thank you to the organizers for inviting me and to also cope with my issues. As Teresa mentioned already, my name is Jennifer Nguyen. I joined the agency in 2006, and for most of my career, I worked in the area of human spaceflight and specifically on medical and psychological research. So I'm very happy to provide you within the next 15 minutes with an overview on what kind of science we support in general in this area, why we support and why we actually need to do this space research. So first of all, what do we do? What is our drive to conduct science and specifically medical or human research in the space environment? Now, you probably have realized it. Human spaceflight is currently entering the next phase of space exploration, or in other words, the second space age has arrived. Almost every day, studies on astrophysics, astrobiology, and space physiology are published in major scientific journals and often make the news headlines. And by the way, at least 4 of the last Nobel Prizes in the last 2 years were related to space sciences. Also, you might have read or heard in the media that all major space agencies, including us from ESA, would like to go back to the moon. We would like to go back there not just for brief visits like in the Apollo program 50 years ago, but this time we would like to stay and work and live up there safely and sustainably. And we would like to do so through what our American friends and colleagues have called the Artemis program. Artemis, by the way, is the twin sister of Apollo. But we do not want to go back to the moon for the pure sake of returning. We would like to go back to prepare and be ready for even more challenging missions. So ultimately, we would like to be able to go to Mars with a human crew for extended periods of time. Now, all those plans sound really ambitious, and they are. But if we want to pursue those plans seriously, we really need to understand the combined effects that space and the space environment have on our astronaut crews and how those combined effects impact astronaut health and performance and ultimately mission success. Just a quick feedback. Can you see my slide?
Yes, we can see your slide.
All right. Thank you. So as of today, only 24 astronauts as part of the Apollo program have been in deep space, and only for a maximum of 12 days. So that means there has not yet been a single astronaut who stayed in space for the total amount of time that is needed for a full mission to Mars and back. And as a matter of fact, only 4 individuals have ever participated in spaceflight missions lasting more than 1 year. But let's face it, once an astronaut crew will have completed the roughly 9-month-long journey to Mars, there is a big risk that they will not be fit enough to carry out all the tasks that they were trained for unless effective preventive measures are developed. So we have an obligation to ensure that our astronaut crew members remain healthy and are able to perform their complex tasks. We have to address as many, if not even all, the risks and challenges if we want to make a mission out of the vision of going to Moon and Mars for extended periods of time. And that is what we do with our daily activities. Now, what are those risks and challenges? It will for sure not come as a surprise to you when I tell you that the space environment does not offer conditions for which we humans were made. Space is actually quite a hostile and unforgiving environment for humans when you think about it. Space exposes the astronauts to massive radiation. It leads to increased risk for cancer. Crews have to live autonomously in isolation and in a pressurized tin can where noise, vibration, temperature are generally less than ideal. And space, of course, exposes astronauts to zero gravity conditions, which has an impact on their bodies. Just to illustrate which effects spaceflight has on the human body, a 6-month stay in orbit reduces bone density by the equivalent of 10 years on Earth. And it reduces muscle mass by 37% over 7 days if we do not apply countermeasures. So all these very extreme conditions have direct impact on the feasibility and the success of those long-duration crewed exploration missions that we are thinking about. And those very extreme conditions are what we address with all our research activities of our human research program. So all the activities that we support through our program center around one central question, and that is, how can we make humans a spacefaring species? How can we contribute to make missions beyond low Earth orbit with a human crew a safe reality? So that is what we do with our daily work. Now, do you actually realize that we do not need to send astronauts to space in order to study how humans, how systems adapt to the space environment? We can actually do a lot of space research without having to leave Earth, without actually having to go into space. So within our program, we make use of very, very unique facilities and platforms, both in space, but also on ground. And each of those platforms addresses or reproduces one or more unique features that are characteristic for the space environment. And each of them provides us with the possibility to address certain risks and challenges that the space environment has on us and the human body. And I will take you now onto a tour through our very diverse and interesting research activities that are part of our program. So I will start on ground and I will move slowly into deep space. We can simulate microgravity effects here on Earth, and we do that in bed rest studies. Bed rest studies are a very well-established model to study the effects of long-duration inactivity or disuse of muscles. So volunteers who agree to participate to our studies, they spend up to 60 days in bed, tilted towards the head end, and by doing so, the bodies of the volunteers start to adapt as if they were in space, and that allows us to mimic and study some aspects of space travel. But what do we actually gain from reproducing those effects? What is our point in making volunteers suffer? Well, we make use of the effects of bed rest on the volunteers to test promising countermeasures. We have tested a lot of different countermeasures in the past, clever exercise devices that we used in bed. We gave the volunteers drugs, special nutrition, but none of those countermeasures have provided us yet with the ultimate solution to counteract the effect of weightlessness on the human body. So the hunt for the perfect, most efficient countermeasure continues. Now, what do you think is the simplest way to counteract the effect of zero gravity on the human body? The answer is actually on that slide. We take gravity with us. Of course, it's not that simple, but we do have tools to create gravity. We can create artificial gravity. Artificial gravity is perhaps the most promising, but interestingly enough, the least studied method for countering the physiological effects of human spaceflight. It has the potential to reproduce Earth-like gravity and to therefore reduce the effects of microgravity on the entire body. We recently put in place a new bed rest study plan that focuses on artificial gravity as the main countermeasure. And the idea is that we would like to prescribe gravity like a drug, giving it in short but large enough doses through so-called short-arm human centrifuges in isolation, but also in combination with specific exercise devices that will be mounted onto those centrifuges. And we are very close to starting those first studies in the very near future. We also support research on the Antarctic continent, specifically on the French-Italian Concordia station. Why are we convinced that research on that station is valuable for us in our program? To put it simple, you can essentially look at Concordia station as an international space station that was dropped in the middle of the Antarctic continent. Concordia station is one of only 3 research stations on the Antarctic continent that are permanently occupied throughout the entire year. The only other 2 research bases with permanent human presence on the Antarctic inland are the American Amundsen-Scott South Pole Station and the Russian Vostok Station. All other permanently crewed bases are on the safe coastline. The closest neighbors from Concordia Station are about 600 kilometers away to the north at the Russian Vostok Station, and that actually makes Concordia Station more remote than the International Space Station. And actually, if you think about it, a stay on Concordia Station resembles a lot the conditions that astronauts will have to face when they are on long-duration exploration missions. They are extremely isolated and confined. Crew members have to live autonomously with the same crew members, with no possibility for resupply for a very long time. And that is why Concordia serves as a high-fidelity analog on Earth for long-duration exploration missions. And we use results from Concordia Station to extrapolate for missions into deep space. In the interest of time, I will not go into detail with this slide. Let me just mention that we also support artificially induced isolation and confinement study, where we look at what isolation and confinement does to humans from a psychological point of view, and we try to identify countermeasure or coping strategies. Another challenge that we need to address when we think about long-duration exploration missions is radiation. Actually, the most dangerous aspect of traveling to Moon or Mars is space radiation. Astronauts on board the International Space Station are still quite protected from space radiation. And even though they are exposed to 10 times more the radiation than here on Earth, that is still much less than the radiation levels that they will encounter during a mission to Moon or Mars. Unfortunately, up until now, we do not yet have good, practical and efficient countermeasures or radiation protection strategies available. And that is why we make use of a couple of ground-based radiation facilities to advance our knowledge in that field. So that is another platform that helps us to prepare for future exploration missions without having to leave Earth. Let me now move a little bit closer to space, to our very popular parabolic flight platform, which is our scientific bridge to the International Space Station. We usually fly 2 parabolic flight campaigns per year. One campaign consists of 3 flights on 3 consecutive days, and during each parabolic flight, 30 individual parabolas are flown. And during each peak of the parabola, roughly 22 seconds of microgravity are achieved. And that allows us to test the effect of microgravity on fast adapting organ systems, for example, on the neurovestibular system. The main advantage, of course, is that scientists can test the microgravity effects with and on humans without having to go through lengthy astronaut training or having to fly to the International Space Station. And the scientists have the possibility to directly modify the experiment setup on board the plane during and between the parabolas. For our parabolic flight campaigns, we now make use of a specially configured A310 aircraft. That plane is now also certified to fly parabolas that correspond to Moon or Mars gravity levels. So now we can also fly gravity levels that correspond to lunar or Martian conditions. But we would not be the European Space Agency if we did not actually conduct research in space. So let's move one floor up to the International Space Station, or ISS. The ISS is the most prominent and most innovative research laboratory that I'm sure you all know. It's the most complex research platform mankind ever made. And we can be very proud to participate to this greatest international project ever. 2 years ago, we celebrated 20 years of permanently crewed ISS, and with that, the ISS is the only and longest running international microgravity research platform ever sustained in human history. More than 100 space flights were conducted over the course of the station's construction period to connect the different modules that had been built on different continents around the world and had never been integrated together until they reached space, which is an amazing feat if you think about it. More than 200 astronauts and cosmonauts have visited the ISS and have contributed to more than 2,500 investigations. Listed here are the European astronauts who have made it to the ISS so far, and who knows, maybe soon Ales Svoboda will also be on this slide. Now, since assembly was completed, a very productive research program has been implemented on board the space station that has continuously grown and will continue to deliver unique results until the end of lifetime of ISS. We may not yet know what will be the most important discovery gained from space station, but we already have some amazing breakthroughs, and I'm convinced that many more will follow because we have just now begun to make full use of all the opportunities that are up there. Our human research program on board the ISS covers all body systems that are affected by the space environment. I know that we do not have a lot of time, but let me provide you with just a few examples. We study the muscle system of our crew members. Because of the weightless environment of space, very little muscle work is needed to move around. And as a result, the muscles of astronauts atrophy and deteriorate in function. So that is something which we really need to counteract against. We know how weightlessness affects the sensory motor system, and you've probably seen that all astronauts experience balance problems immediately after landing. And that is of concern once astronauts land, for example, on Mars, where one of the key questions is how long after landing will it take the astronauts to recover, and will they be able to perform the required mission tasks? Also, food and nutrition are important parts of our lives. We all know how an energy deficit can affect our moods, our ability to function and to think properly. So we all need food to provide us with sufficient nutrients to meet our metabolic requirements. But we also know that those requirements are not met by crew members who are on board the ISS. We do not know why. Is it because astronauts have reduced appetite? Is it because taste and smell sensations are changed? Is it because energy requirements of astronauts in space are changed? Do astronauts need less calories when they are in microgravity? So these are some of the questions that we address with our human research program. There are many, many more. These were just a few highlights. Now, I took you on a tour through our various research opportunities. I started down on ground. I continued in low Earth orbit. Let me now move beyond low Earth orbit to the vicinity of the moon, or to the Gateway. Now, what is Gateway? I told you already earlier, all major space agencies are preparing to put astronauts on the lunar surface within the Artemis program. But contrary to what was done 50 years ago within the Apollo program, this time astronauts will first dock with the Gateway before boarding a lander that will then carry them all the way down to the moon. So the Gateway is going to be a moon orbiting research platform from which a lot of research will be performed. Of course, the Gateway still needs to be assembled in lunar orbit, but once all those pieces are put together in orbit, we will have the infrastructure that we need to send astronauts to the lunar surface. And NASA and all international partners are confident to be able to do so by the middle of this century, of this decade, sorry. You've probably heard or read that 2 weeks ago, the first uncrewed mission of the ambitious Gateway or Artemis program was launched. That so-called Artemis 1 mission serves as uncrewed test flight and will soon be followed by crewed flights to the moon. So far, the Artemis 1 mission is going very well. We expect Artemis back in December. Before it returns back to Earth, we will probably be treated with many more amazing pictures from Earth and Moon. And I'm confident that we will also soon be treated with amazing science opportunities off and on the moon. And then finally, we also support activities that do not fit into the box, that do not fit into our traditional research platforms, but which are nevertheless innovative and very exploration relevant. So let me close with 2 examples. When you think about the scariness and all the challenges and risks of space and the space environment, then you probably do not think of dust and specifically moon dust. But dust is much more dangerous than you may realize. Because of the lack of gravity, dust never settles. So imagine breathing all the dust in, with each breath 1 million tiny particles, and think about the damage it can do to your lungs. Dust is made of tiny sharp grains. It can be as rough as sandpaper and can therefore do quite some damage. In addition, dust is a very fine powder that can stick to everything it touches, and it can find its way into basically everything, including, for example, your spacesuit. The crew of Apollo 17, they learned their lesson of how dangerous moon dust can be. After their moonwalk, they were so eager to leave the moon surface and go back to their lunar lander that they forgot to brush the dust off their spacesuits and boots before re-entering the space capsule. The dust clogged up their suits, it spread all over the spacecraft, and they were then stuck with it on their journey home. That moon dust gave rise to the now famous Apollo aroma, and all crew members soon complained of nasal congestion, a phenomenon that we now call lunar hay fever. So the topic of lunar dust, or dust in general, is something where a lot of scientists are currently trying to develop models and strategies on how to mitigate the toxic effects of dust in space. Then let's finish with something that may sound crazy at first sight, but it's actually not, and that is putting astronauts into long-duration sleep. Now, in clinical practice, for more than 2 decades already, the concept of torpor, or temperature management, as a therapeutic tool has been applied already. There are protocols in most major medical centers for inducing hypothermia in patients to reduce their metabolism, to basically gain time during surgeries, and also to keep the patients in a better shape than they would usually be after such interventions. Torpor, or hibernation in general, is characterized by a reduction of metabolic rate, and it goes along with a controlled decrease of body temperature, a suppression of body function, and leads to suppressing the metabolic rate well below the normal metabolic rate. And we plan to build on this natural phenomenon and actually support this activity within our program. So we would like to find out where in the brain or nervous system is hibernation initiated, through which messengers or agents is it initiated. And once we will have identified how to initiate torpor or hibernation, we plan to induce daily or seasonal torpor in animal models that usually do not undergo hibernation. And ideally, this activity will allow us to induce torpor in astronauts with some of the very nice side effects that are listed here on the right side of the slide. So you see, we have exciting times ahead of us. Let me repeat what I mentioned at the very beginning of this talk. We will continue to use low Earth orbit for research, but we have new initiatives on the horizon. Our vision is firmly set on the moon and then on Mars, and we have a lot of work to do to get us safely to Moon and Mars. I admit missions to Moon and Mars with human crews continue to sound like science fiction material, but we will go to Mars within the next century, of that I'm sure. Just think about how normal it is nowadays to board a plane and fly over across the ocean to another continent within a day. Had we lived 100 years ago, we would not have believed that this is possible. And the same is and will be true for missions into space. I hope you share my passion for our fascinating program. We humans, we may not have evolved for life in orbit, but learning to live up there helps us a lot about staying healthy on Earth and improves many processes in daily life. And with that, I would like to thank you for your attention. Thank you for your patience. And I'm available for questions if there are any.
Thank you, Jennifer. That was really an eye-opening talk. We are a little bit over time, but hopefully we can, make up for it somewhere else. Is there someone who is dying to ask a question? Anybody? Okay, so it seems that nobody's really dying to ask you questions. I think they have to still take it all in. So thank you very much for being here with us, and I hope you get over your COVID infection soon. Thank you for your time. So that was Jennifer and Goan, and we are now going to move to the next section, because obviously space is not just about astronauts. There is so much more to space than just a human spaceflight. And to make the most of all the opportunities that space presents, we need proper space education and research. So in the following segment of our program, we will hear from the leading Czech science and research institutions and universities about their approach to education and research in space. So there will be 6 presentations, I believe, and each of them will last about 10 minutes, and at the end we will have some time for questions and answers in case there are any. So I would like to invite our first speaker, and that is Dr. Robert Popela, who is an assistant professor at the Aerospace Department at the Faculty of Mechanical Engineering of Brno University of Technology.
Thank you very much. So good afternoon, ladies and gentlemen. I'm just waiting for presentation, which is not yet on Beamer. Thank you. So today I would like to speak about education and partially research at the Brno University of Technology, because as it was mentioned by other speakers, there is a now quite big boom of space research and industry in the South Moravian and overall the Czech Republic. And we are one of the major institutions delivering space engineering education. So if we can go to the second slide. Short introduction. The Brno University of Technology was founded in 1899. It has almost 22,000 students yearly who are victims of our education process. We have like 2,900 employees, and the university consists of 8 faculties and 3 separate institutes. From 8 faculties, 3 are directly connected with space research and education. I will go through each faculty competencies and study programs. Please, next slide. So those 3 faculties which are engaged widely in space research are Faculty of Mechanical Engineering, offering Master of Science and PhD program related to space, Faculty of Electrical Engineering and Communication, and the Faculty of Information Technology, mainly with PhD program, but generally the information technology is a part of space research and education directly. The core of research activities is focused on European Space Agency programs and projects. 3 most important parts of education are the experience of lecturers, the funding, and the motivation of the students. I said the experience of lecturers, not the knowledge or education, because the expert is the person who already passed a lot of failures and got lessons from previous projects. For that, it's very important that the university is widely engaged in practical research programs and is collaborating directly and tightly with the industry. Technical universities are generally applied universities, and our task is to deliver to industry skilled engineers who can now enter new field of engineering, because my feeling is that in the Czech Republic the last 10 years are important in increasing involvement in space research. So, the composition of presentation is that I would like to present highlights of most successful research projects and their reflection. Yeah, thank you. And their reflection into the education process. So the first is a Faculty of Mechanical Engineering and directly Institute of Aerospace Engineering. The most interesting project of the last years is European Space Agency project led by the Thales Alenia Space as a prime, and we are the member of consortium, our institute, who is responsible for integration, mechanical design and testing of the moon drone studied in a part of feasibility study in the Earth conditions and its redesign for the moon conditions. You can see on the pictures the vehicle which were designed, manufactured and assembled at our institute and was tested at the Jihlava test range. The second very interesting project where the Brno University is already prime, so it's a contractor of European Space Agency, is the development of miniaturized heat switch for probes and satellites. And the task is to develop most powerful heat switch which is able in space conditions to perform the interconnection between cooled electronics and heat sinks without any external delivery of energy. So the switch is designed on the ground in a way that its behavior is pre-programmed by the selection of design and materials. Another example from Faculty of Mechanical Engineering, DEFINT Institute, Energy Institute, is design and manufacturing of habitats for extreme environments. Those habitats are simulating stations for the ground or earth conditions tests of human stay in the moon conditions. The study program at the Faculty of Mechanical Engineering is divided in a Master of Science program and PhD program. Those two programs are reflecting the needs of space industry, And in a Master of Science program, the aerospace technology, particularly including the specific courses on space structures, space flight mechanics, and spacecraft technologies is involved. And our applicant, or the applicants of study program, after study are entering career in many companies. So most of you are aware that in the Czech Republic there is OHB, SAP Aerospace, VZLU, Honeywell, and other companies. And on a Monday I visited the Space to Business event in Prague, which is similar event but focused mainly on industry. And I met at every second exhibition of companies students who ended our Master of Science program at our institute. The PhD program in aerospace technology is focused on widening education of students, and they are directly engaged, and PhD thesis topics are coming from industry collaboration. So the examples above, there was a huge involvement of PhD and even sometimes master students. The second is Faculty of Electrical Engineering and Communication, particularly Department of Radio Electronics and their experimental satellite laboratory. You can see very impressive images because the technology developed at the department was implemented on practical missions within the EMSAT Phase 3D satellite and PCSAT US Naval Academy project, which spent also 1 year at the International Space Station during 2005. The second interesting stuff is the high throughput wireless communication developed for aerospace applications based on a communication with satellites in the L-band. The department is collaborating on the European Space Agency project led by Inmarsat together with company Honeywell. So the Faculty of Electrical Engineering has opened in a recent time Space Engineering Program, Space Apps, which is international master's study program. All courses in English. Applicants can come from any country. It's the only master's degree focused on space in the Czech Republic, which is accredited and is purely dedicated to space engineering. It's a kind of multidisciplinary program, so the students are taking part of the lectures at the Faculty of Mechanical Engineering at our institute. So we are preparing courses on mechanical engineering in space applications and other technologies. Meanwhile, the Faculty of Electrical Engineering is focused on electronic devices design, communication, and other stuff. So in the 2022, already 30 students applied for this program. And if I'm correct, even if the lights are quite strong, I can see some students of that program present here, so they are really interested in the topic. The third, last but not the least, is the Faculty of Information Technology, which is focused more on software, less than the hardware of the space technology. Here you can see example of their highlighted project, which is Hera mission of Milani CubeSat, where the advanced compression and noise reduction for hyperstructural images data was applied. The project is focused on visual inspection and dust detection of Didymos asteroid following DART impact. As you probably noticed, this mission was successful and the impact was or reached the goal. So this technology or software analysis of the images was performed at the Brno University of Technology. The Faculty of Information Technology does not have distinguished space engineering program. The study programs are generally focused on specific topics which are directly applicable and are inherent part of current space research. Machine learning, computer graphics and interaction, cyber physical systems, and software verification and testing, which is very important in space applications due to high requirements on reliability and certification of equipment. What is the future of space engineering education at our institution, and maybe comment on general conditions in Czech Republic? So university and universities generally are reacting to demands of industry because the feedback from the companies is that there is a really huge demand on skilled engineers with the increased number of the projects with Czech participation. The widening of programs and more multidisciplinarity in programs, which means that, as was the example, we are trying to interconnect pure mechanical design, electrical design, information and communication. And we would like also to increase the quality of the research and industrial cooperation experience. Below the picture you can see the test firings of moon drone vehicle. That was all from my side, and if you have any questions, I'm available to answer now.
Thank you. Our next speaker is Professor Zdeněk Němeček from the Faculty of Mathematics and Physics of Charles University in Prague. I would just kindly like to ask the speakers to try to stick as much as you can to the 10 minutes limit, because we're running quite a bit over time. So thank you very much.
Dear colleagues, ladies and gentlemen, it will be, please next slide, it will be a very difficult task to introduce the space activities at Charles University, because as you know, Charles University is the largest university in our country. There's about 50,000 of students, and we have about 600 of different study programs, but none of them is devoted specially to the space research or space activities, because we believe that the universe, we are part of the universe, and it means that universe is a natural part of many of our study programs. Among the faculties we have, there are three which are in some sense deeply connected with space research. It's Faculty of Science, Faculty of Mathematics and Physics, and maybe it can be a surprise for you, Faculty of Law. Yeah, but actually space law becomes more and more important. We have the problems with occupation of the geostationary orbit. We have problems with space debris. And we will have, in near future, we will have problems with adoption of moon or with adoption of Mars. As I noted, there is no special space-oriented study program, yes, but you can see examples at bottom. You can see examples of, say, PhD theses which are currently solved at Faculty of Mathematics and Physics, and you can see that they are clearly connected with the space research. And now we will start with different activities. It's Faculty of Mathematics and Physics, Department of Surface and Plasma Science. Maybe some of you know it as a Department of Electronics and Vacuum Physics. Yeah? And this department is involved in space research for more than 50 years. You can see the first device which was launched in 1971. On the left, on the right, you can see the last device. It's not our last space activity, but it was the last device which was completely developed and manufactured at our faculty. As I noted, we are in space for more than 50 years, and we are interested mainly in solar wind processes, interaction of solar wind with planets, planetary magnetospheres, or space weather. We will go to space plasma processes. You can see the examples of our activities, which are investigation of solar wind ion composition, interplanetary shocks, and when the solar wind comes towards the Earth, it interacts with Earth's magnetic field, create a great cavity called magnetosphere, and we are investigating the boundaries of this cavity, like bow shock, forest shock, magnetopoles, cusp, or processes like turbulence in the solar wind or reconnection of magnetic field lines. Maybe it was already here mentioned that dust in space can be a relatively big problem sometimes. Yeah? And the problem is we are at places where the gravity is low, and in such a case, the electromagnetic forces, because this dust is charged, can be very important, but it cannot be investigated in space. For this reason, we are running the laboratory equipment for investigation of the dust charging. And we are also trying to use, because the dust detectors are real dust detectors in space, on satellites, are very large, very, say, expensive, and maybe not so productive, because the entrance window of such detector is very low. For this reason, we are using, for detection of the dust impacts, we are using the whole spacecraft. You can see the example here. Or we developed some technique to register dust impacts by Faraday cups, standardly used for measurement of the, say, plasma parameters. And for you, it is on the left-hand side. On the left-hand side, you can see very nice example of results connected to the students, because here you can see the charging of the dust cluster composed of dust grains of different diameters. And this is the work which was done by our PhD student. And you can see there is very nice invention, because you can see the shape of this dust cluster, which resemble the shape of our mascot of our laboratory, Professor Vítek. Another topic we are dealing with is investigation of processes occurring in interstellar medium. It's not accessible now for, say, spacecraft or some missions, but we can simulate it in the laboratory. And you can see one example of such apparatus and some results, which can be in some sense surprising. In deep space, you can have very low temperatures. We are able to work at temperatures close to the liquid helium. And you can see, for example, on this graph, that surprisingly, instead of standard water, H2O, you can have, in this case it's heavy water, H2O, but you can have the 3O. Now we are going to Department of Geophysics. They have master physics programs, but again, nothing is devoted only to the space research, but we have a lot of courses which are connected with the space research and which can help to the space research. You can see some examples here. They are investigating moons of giant planets, which can be investigated only by, say, computer modeling, using the data from the spacecraft. And on the right-hand side, you have application of the near-Earth satellites, measurement of near-Earth satellites for determination of the conductivity of the Earth's mantle in different ways. Now we are going to the Department of Applied Geophysics and Cartography, and with Faculty of Science. They have a lot of bachelor and master courses, but what I should mention is transatlantic training workshop, which is organized each year, and many students from different countries participate in this workshop, which can be devoted to many topics connected with space, which are listed below. And what they are using usually the satellite data from low Earth orbit, and they can monitor many things like forest disturbances and so, which are very important for say, our agriculture or industry. And another institute is Institute of Hydrology, Engineering, Geology, and Applied Geophysics, which are trying to teach some not conventional methods in geophysics. You can see the list on the left-hand side, and you can see, for example, very interesting application, because they are looking at the source of water of the Mars on the moon surface, and they found that there is a possibility that part of this water on the moon surface can be of the Earth's origin due to the water which comes from the Earth's atmosphere to the plasma sheet, and when moon is crossing this, they can found it. I can see that my time is up, but the last point here is again the investigation of impacts from the space on the Earth and what can happen. If you will have more questions, Kolega Kletečka is here and you can ask him. Thank you for your attention.
Thank you very much. Thank you, Professor. Our next speaker is Dr. Robert Filgas, who is the head of the Department of Experimental Physics and also the head of space projects at the Czech Technical University in Prague.
Thank you for the introduction and for the invitation. I'm here to present space education and research of the Czech Technical University in Prague. After the Brno presentation, I'm not so sure about the first statement, so let's just agree that CTU is one of the largest and oldest technical universities in Central Europe. We have over 17,000 students, 8 faculties and 6 institutes, one of which is my institute. Institute of Experimental and Applied Physics. We have over 200 degree programs. So here is an example of lectures that are directly connected to space research, which our students can attend. So of course, at the Faculty of Electrical Engineering, they can attend space engineering, so designing electronics, sensors, instrumentation, learn about astrophysics, space sciences, and technology. At the Faculty of Mechanical Engineering, there is a lot of material sciences, aerospace materials, numerical methods in aircraft and space engineering. aviation, cosmonautics, and so on. At the Faculty of Nuclear Sciences and Physical Engineering, they can learn about astroparticle physics, astrophysics, astrochemistry, and radiation, which we saw at the ESA presentation is very important in space. Also at the Faculty of Transportation Sciences, they can learn about instrumentation system in aircrafts and space vehicles. Of course, these are just examples directly connected to space, but there are a lot of indirect application of things that students can learn at Czech technical universities. I recently met a colleague from Faculty of Architecture, which is working on designing space habitation modules for lunar and Martian surfaces. At the Faculty of Nuclear Sciences and also at our institute, you can work with radiation detectors, methodology of radiation detection, protection of both humans and components. So there are a lot of hidden applications, let's say, that you can then use in space research. So that was about education. Now some space research at the Czech Technical University. I'll start with national programs, Gacher and Tacher. I guess we are mostly Czech, so I don't have to explain what those are. There are too many projects to list. So just an example, CTU, namely Faculty of Electrical Engineering, our institute, and Faculty of Nuclear Sciences was a part of the consortium that developed VZUSat-1 and VZUSat-2 successful satellites. We are also, Czech Technical University is also part of prestigious Horizon European Commission programs. So Faculty of Electrical Engineering is part of AHEAD and AHEAD 2020 programs, which is an international network of high-energy astrophysics communities. Our institute is collaborating on PAN, which is a magnetic spectrometer developed to detect high-energy particles up to 20 GeV in space. I, of course, have to list ESA programs. So since 2009, this is where our records go. CTU was prime in 23 ESA projects. So 9 were led by Faculty of Electrical Engineering, 8 by our institute, 5 by Faculty of Nuclear Sciences, and 1 by Faculty of Civil Engineering. There are 2 ESA projects currently running where CTU is prime. Both are led by our institute, me specifically. One is Radiation Monitor System in Package, which is a development of a small all-purpose radiation monitor. And then Radiation Environment Monitor for Energetic Cosmic Rays, which is one of the ambitious projects. Speaking of those, CTU is part of 3 of these Czech ambitious projects or missions. As I said, REMEC is directly led by Czech Technical University, and it's about monitoring of high-energy particles in deep space. CTU is also subcontractor in Lvice 2, which is about measuring solar wind in lunar orbit and dust in L4, so another deep space mission. And Faculty of Mechanical Engineering is a subcontractor in CZ-ARM project about research and development of robot components for use in space. Of course, these were all where CTU was prime, because those are easily findable in our system, but there are a lot of hidden gems where CTU is participating as a subcontractor or other participating somehow else in missions. So those are hidden gems which are mostly not listed in our system, so I had to rely on information from deans and so on. So namely some examples, Faculty of Electrical Engineering is part of several big ESA missions like SMILE, Theseus, and Athena, mainly concerning X-ray astrophysics. our institute, we celebrated last month 10 years on board ISS with our radiation environment monitors. In May next year, we will celebrate 10 years of our SATRAM radiation monitor on board Proba V, which we developed together with BD sensors. This is all great heritage for us. Thanks to this heritage, ESA and NASA chose our detectors to be on board outside and inside of Lunar Gateway to monitor the radiation on the outside and also inside the station. So you can see, you can see 2 units here. CTU also organizes space-oriented conferences and summer school. So with details, René Hudec can give you a lot of details regarding that. A lot of us go attend AXRO and SPIE conferences, also IBEWS at Karlovy Vary. There are some summer schools that they organize as well, so there is a lot of outreach of CTU. So summary, as you could see, Czech Technical University is very active in space research and education, including PhD studies, because those that I presented were bachelor and master studies. So again, at the Faculty of Electrical Engineering, you can do your PhD in space engineering. At our institute or Faculty of Nuclear Sciences, you can do PhD regarding space radiation. We are very successful in national, European Commission and ESA space projects. We are participating in CubeSat missions, rocket flights, large satellite missions of ESA, NASA, JAXA even. We are on board both space stations, and CTU now has the potential to launch its own deep space satellite mission. As you saw, space research at the Czech Technical University is dominated by Faculty of Electrical Engineering, which is frankly not surprising. I guess that's something similar in all universities. And our institute, together with the Faculty of Nuclear Sciences, because we have quite a name in space radiation monitoring and detection. So more details on Faculty of Electrical Engineering space activities are on this page. And thank you for your attention.
Thank you. Thank you very much. And our next speaker is Tomáš Řezník, who is an assistant professor of geography at Masaryk University in Brno.
Ladies and gentlemen, good afternoon. I'm grateful to the organizers for this invitation, and I would like to follow up a keynote speech that has been by our Dean of the Faculty of Science, and I would like to go a little bit more into deep and more narrow-focused presentation on research and also education at the Department of Geography. In fact, my keyword phrase would be down to earth, because we have 3 study programs dealing with Earth observation, as you can see. We are a very active member of Copernicus Academy initiative, and we have experience with dozens of Horizon Europe projects or their equivalent starting from FP6. Our activities are very closely touching the international relations, because I have been a consultant at the United Nations responsible for the global soil information system development. My role has been to set up a foundation, to set up a data model for global soil information system, which comprises also soil sensing. So that's the reason why we are using also and following space. My former employer has been the European Commission, the Directorate General Joint Research Center, and we have quite a lot of common research also together with the JRC. And our cooperation with NASA has been very intensive. In the past, we have been a part of the Architecture Implementation 8 on water pollution monitoring at Global Earth Observation System of Systems. And right now, for the last 3 years, we are continuing with Earth Science Information Partnership that is being founded by NASA. The educational activities, just in a nutshell, as you can see, comprising the Master of Science lectures with basic principles, image classifications, image processing, etc. At the PhD level, we have one specific course. In fact, it's one specific course out of 4, because we have rather an ad hoc research-oriented PhD study. And we have also a learning course on Copernicus, on European Earth observation. And of course, in line with that, we do not have only classical education as we all know it. We are focusing on popularization through several activities like Night of Scientists and several activities for younger students than we are used to, or older students than we are used to, as well as to primary and secondary schools that we have also together with ESA, the cooperation. I would like to share with you one research showcase. It's my passion, I have to say. The goal of that is to reveal, at least partially, the memory of landscape. So, as a ground truth, we are using sensor measurements. We are following precision agriculture approach. We are monitoring second by second movement of vehicles. Within each second, we get up to 60 parameters, up to 60 attributes. For instance, speed of a vehicle, yield moisture, fuel consumption, etc. And the Earth observation is for us a proxy how to upscale our research. So for that reason, we are using typically 8 years series and trying to distinguish where the high and low yield productivity zones are. So the areas with considerably higher yield than the average of a field, or a lower one. And as we are at the Faculty of Science, it is clear that our passion is environment. So for that reason, we are trying to have some kind of guidelines, some kind of application, like lowering the amount of nitrogen, for instance. A very technical one to optimize 3D trajectories, or trajectories in 3D. In fact, from a mathematical approach, the most common task is painting of a submarine. And in fact, it has the same mathematical basis. And if we have the areas that are very low productive, for instance, within the past 8 or even more years, we have a very simple question with a common sense. Aren't those the areas that our predecessors already knew, and for that reason they use them as a wetland, they use them as, for instance, a bush or anything else. So this is research we are trying to have. In fact, if I will share with you preliminary results, it seems like the memory of landscape is like a human memory. 2 generations and it's gone. So even very drastical things that we do to the nature are being forgotten if there is not a stress from water. Just a brief thesis overview. We are using a lot of missions. Very commonly, we are using Sentinel and Landsat, for instance, in the data comparison, and the same we are using for biomass and yield changes. But on the other hand, we are using also the PlanetScope. As you can see, we are using the radar-based modeling. We are following the CASI sensor for chlorophyll classification or forest detections, or as you can see, also the landscape changes, where we are combining satellite images with aerial images, where we are very lucky because thanks to military archive, we have the images starting from 1937, as you can see. So quite a long time series. So my first part of the presentation, in fact, was the majority. I would conclude, may the geo be with you, and also down-to-earth applications be with you. I don't know if there will be the continuation of the Professor Dobrovolná in this presentation, because there's more to offer at the Faculty of Science, in fact, much more related with space. I've just right now talked about the applications that are directly related to our department. But I'm very proud to have you the very brief introduction of Professor Dobrovolná's team that will be presented in one of the following sessions. She will directly continue with what has been mentioned with the ESA keynote about human activities and also impacts that are being researched and explored. So thank you all, and I'm curious for all your comments, questions and remarks.
Thank you very much. And next we have Dušan Mandat from the Palacký University in Olomouc.
Good afternoon, ladies and gentlemen. Okay. So I'm here to present our activities in the space or astroparticle research at the Palacký University. So actually there is no dedicated study program at the University of Palacký, but we have two departments where we do research. In principle, the first one is the Department of the Optics, and the other one is Joint Laboratory of Optics. So here we can see the list of a project that somehow deals with the universe or astronomy or astroparticle research. So the first one is the Department of the Optics. So what they do mainly like theoretical research. So they do super resolution. So this is mainly connected to astronomy, where you have like nearby sources, and you can, if you want to somehow distinguish those two sources from the image, it's really very complicated, and you have also some criteria which limits the separation between two sources. So this is the let's say theoretical research that they are dealing with, or they are studying. The other one is quantum optics, mainly quantum cryptography, and they are also involved in this project Skylight, and they are trying to to use the quantum cryptography using the satellite and use the let's say secure transfer of the information with using the quantum cryptography. The second department is the Joint Laboratory of Optics. So it's a joint project of University Palacký and Institute of Physics of Czech Academy of Science, and we are a member of different observatories and international projects. So the first one, the most important, is the Pierre Auger Observatory that is already running for more than 20 years, and it's located in Argentina, close to Andes, and there we are measuring very high energy particles with these energies, and we are using two different techniques. One is the fluorescent technique. The primary particle interacts with the atmosphere and creates secondary particle, and also the fluorescent light, and we are using the optical telescopes to measure during the night the fluorescent light, and also we are using the surface detectors. So Pierre Auger Observatory is actually the biggest observatory on the Earth. It covers more than 3,000 square kilometers. So we have 4 fluorescent telescope stations here. And actually our laboratory built more than 1,000 of the segments. So these are our fluorescent detectors. So they were produced, the mirrors were produced in Olomouc, and we do we produce the mirrors, we also code them and install them, and we do care about the optics or the telescopes. So this is the opportunity for master and PhD students. So in principle, they can use the data that were measured at the Pierre Auger Observatory. They can do the simulation data analysis, energy spectrum studies, or mass composition. The other project, big international project, is the Cherenkov telescope array. Here we do measure the gamma rays with lower energies than the Pierre Auger Observatory measures. There will be two observatories, one at La Palma, the other one close to Iso in Chile. And there will be 3 different optical Cherenkov telescope. The biggest one is LST, with the primary mirror diameter 24 meter. The other one are MSTs and small size telescopes. So our involvement is within the optical simulation. We are also now developing back-coated mirrors to increase the lifetime of the mirrors. Then we do some optical measurements. We do alignment of the big telescope, and also the maintenance, and we also measure or we deal with the sky quality monitoring of the observatory. Here you can see this is the prototype of the back-coated mirrors. So in principle, most of the observatories, they use the mirrors where the substrate is coated on the front surface, but those telescopes will be outside, so the coating will be exposed to the environmental conditions at the sites. So the temperature will change, humidity, and there will be also dust and sand, this could affect the coating. So now we are developing like a back-coated mirror, so it means that the reflected layers are at the back of very thin glass. So this will increase the lifetime of the mirrors. And here you can see this is the picture of the LST telescope camera. So it's really extremely big. We also are a member of the SST1M project. These are small size telescopes which measure the Cherenkov light and the gamma rays. And here I think it's a very good opportunity for the students, because we have 2 telescopes installed in Ondřejov, which is the observatory close to Prague. So the instrument is there. Sorry, we have 2 telescopes there. So we already commissioned them, or there was like 2 years of commissioning, so we already operate the telescopes. Here you can see the first light, the muon ring, and the shower from the high energy gamma ray photons. So this is another picture of of one of the 2 telescopes in Ondřejov. This is the camera of the telescope. It's actually 4-meter diameter telescope. The mirrors were produced in Olomouc, and we are responsible for the operation, for the maintenance. And here are the opportunities for the students. So they can be involved in the simulation, for example, atmosphere, night sky background, and so on. Data analysis. We are now starting the stereo observation. So we are now developing like the trigger mechanism using white rabbit, and also the students, they could be involved in the optics, like producing the mirrors, measurement of the mirrors, and also alignment of the whole telescope, and the long-term operation, because the telescope will stay for few years in Ondřejov. Then we are also doing like auxiliary systems, for example, the all-sky cameras, because for those experiments, Pierre Auger Observatory and CTA, we need to know the condition of the sky. So we developed in Olomouc these all-sky cameras where we can measure the cloudiness, like using the astrometry to checking the visibility of the star, but also the photometry. So we can in principle like roughly measure the extinction of the atmosphere, and then provide the information for the data analysis and for the corrections. Also, for example, here kind of example for Pierre Observatory, like kind of photometrical measurement, and this system decides or check the operation of the observatory, and the shifters, they can check where they can open the camera, the telescope, and see if they will not destroy the PMTs of the camera. The other projects is a fast. So this is like a small or new generation of a small fluorescent telescope that will be like a new replacement of the Pierre Observatory of or TA. The idea is to have really, here you can see it's fluorescent detector array of single pixel, but actually we have 4 pixels. These are the picture of our telescope installed at Utah and Argentina. So we covered both south and north hemisphere. Actually this is the first Czech fluorescent telescope. So it was completely designed, produced, tested in Czech Republic in Olomouc. Here you can see, for example, the new mirrors. We are now developing the hot slamping technique to completely, or to make the process much faster. So we do not grinding and polishing the mirrors, but just hot slamping the shape, and then we are coating the mirrors. So the idea is to have like a few pixel telescopes, and a lot of them covering a really big area to increase the statistic of the detection of the high energy cosmic rays. And from the geometry and from the time or intensity profile of the data from different stations, we can then calculate the energy and the trajectory. So here you can see the opportunities. So the telescope is in our hand. Only the DAQ, the electronics is made by the Japanese partner, and also the PMTs are from Hamamatsu. But we are still in the state of development of this instrument. And now we are building the new enclosure because we want to start to make like a grid of the telescope, and hopefully we will install it in Argentina next year. Also, we are a member of the SWGO, which is which will be the observatory, the full sky observatory to detect high energy gamma rays, because the CTA use the optical telescope and they are really observing the sources, but this will be the full sky or almost full sky observatory. Will be based on the water sharing of tanks. And now we are in the phase of developing the detectors, the DAQ software or whatever, and also we are now searching for the best site to install the telescope. So for example, these are also the instruments developed and produced in Olomouc, and we deploy them to the candidate site, and now we are trying to find the best site for the SWGO. So thank you for your attention.
Thank you very much. And our last speaker before the coffee break will be Lucie Kolesníková from the University of Chemistry and Technology in Prague.
Thank you very much. Okay. At the beginning, I would like to introduce the field of molecular astrophysics, which is closely connected to our research we do at the Department of Analytical Chemistry at the Faculty of Chemical Engineering at the University of Chemistry and Technology in Prague. Molecular astrophysics is a field which deals with observations of molecules in space and uses molecules to determine physical conditions of the emitting gas and also its chemical composition and also the chemical evolution of the gas. It basically relies on 3 main pillars: on astronomical observations using radio telescopes, then on astrochemical modeling and laboratory experiments. Of course, laboratory experiments encompass a broad range of experimental techniques, and among them, I would like to highlight rotational spectroscopy. It's a technique which has been proven very suitable to decode molecular universe. And why? Because each molecule has completely different rotational spectrum. It is even possible to distinguish between different conformers or structure isomers or even isotopic species of a single compound. So it is very, very powerful tool. To date, it has been discovered in space over 200, oh, sorry. Okay. Sorry. Over 270 chemical species, and from them, nearly 230 were discovered by means of rotational spectra. Rotational spectroscopy deals with samples in gas phase, and the only requirement we need to observe molecules by means of rotational spectra is that the species needs to have permanent dipole moment. Rotational transitions are observed in this frequency region, approximately between 2 GHz and 1 THz, so we are situated between radio frequency region and infrared region. At our university, we have 2 spectrometers that are able to measure rotational transitions. First one deals with lower frequencies from 6 to 26 and allows to measure molecules under specific conditions, under cold conditions, for example, using supersonic expansion, so we are able to capture very, very unstable compounds. The second spectrometer is this one. It works up to 700 GHz, so it provides a really broad and comprehensive spectral characterization of molecular species. We are able to analyze isotopic components or also excited vibrational states. These spectrometers are home-built, they are unique in the Czech Republic, and have been configured during many, many years. The head of our laboratory is Professor Stepan Urban. So if you have any questions or you would like to be interested to collaborate with us, you can contact him. So as I said, the spectrometers work really in a broad frequency range from 6 to 26, from 6 to 700 GHz, which is actually the frequency region which overlaps with many astronomical facilities. I would like to highlight, for example, ALMA, Atacama Large Millimeter Submillimeter Array, which a set of over 60 antennas, which works together like an interferometer, working in this frequency range. Well, our instrumentation also overlap with several single-dish telescopes like YEBES or IRAM, which are situated in Spain. So our data directly compare with data that astrophysicists observe by means of radio telescopes. Here I would like to show you the importance of laboratory experiments. This is a spectral survey which is obtained from IRAM telescope, and it is focused on Orion, Kleiman-Low Nebula. Here in this part of the figure, probably you cannot see too many signals, so it seems like there is nothing, but the opposite is true, because when we amplify the y-axis, you can see that there are thousands of lines. And how to interpret these lines? Well, we need to do before laboratory measurements. And especially nowadays, when there is a continuous increase in sensitivity and detector bandwidth of observing facilities, so more and more signals are observed. And we don't know what molecules are responsible for these signals. So therefore, we need to do laboratory experiments. So at the University of Chemistry and Technology, at our laboratory, in the Department of Analytical Chemistry, we follow this strategy. First of all, using astrochemical networks or other tools, we need to find molecules to study. Then we measure in our laboratory rotational spectrum. Of course, many of molecules are not stable in laboratories, so we need to develop specific techniques to generate these species. When we are successful in this, we record the rotational spectrum, and then we need to assign and analyze the spectrum. This is also done with the help of theoretical calculations. Once we analyze the spectrum, then we are able to simulate the spectrum under certain conditions of interstellar medium. Then we compare our simulated spectrum with real line survey, which is captured by radial telescope. And if there is a match, then the molecule that we studied before in laboratory is really in space. And what happens then? The new molecule can be again introduced into astrochemical model as an input. And from this molecule, more molecules can be actually produced, and we can study these molecules again. So in our laboratory, we basically study molecules of astrophysical interest. Our students actually deal with these spectrometers that I introduced. They learn how to manage latest microwave instrumentation. They learn how to measure the spectra, how to interpret the spectra, and how to obtain the predictions which are useful for astrophysicists. Once we have the predictions, we collaborate with many people from other institutions, for example, from Max Planck Institute for Radioastronomy in the context of chemistry of high-mass star-forming regions. But of course, we also deal with other institutions from Centro de Astrobiología from Spain, and also with University of Toulouse, University of Copenhagen. But we collaborate not only in the context of astrophysics, but also in the context of laboratory measurements and analysis with many other institutions. Well, once the molecules are detected, then it is possible to obtain many informations about the physical and chemical conditions. We can, for example, derive molecular abundances, what is the isotopic ratio in given part of interstellar medium. Also, we are able to derive excitation temperatures, source sizes, and so on. Another interesting topic is to deal with prebiotic species, which are molecules that are thought to be involved in the chemical evolution on early Earth, which means with the origin of life. For example, amino acids are really important target in this part of astrophysics and astrobiology. Of course, also our students learn how to generate very unstable species in the laboratories, and also learn how to predict rotational spectra and how to predict other properties of molecules. Here I would like to show you some topics that we offer to our students within bachelor and master program. For example, Professor Urban offers a topic related with determination of temperature of interstellar clouds, or even movements of the interstellar clouds. Or, for example, the measurements of isotopologues of different interstellar species. I have also several students that deal with, for example, nitrogen-bearing compounds that could be present in the interstellar medium, or sulfur compounds. My colleague does rotational spectroscopy of heterocyclic compounds, and so on. So students deal with these experimental techniques to learn rotational spectroscopy and how to obtain predictions that serve to astrophysicists to decode molecular universe. Thank you for your attention.
Thank you very much. We were supposed to have a Q&A session now, but we are running something like 20 minutes over time, so we will go straight into the coffee break, and I will see you here back in 15 minutes. Thank you very much. everyone, welcome back. It's good to see that you have all stayed with us. We will start the next section of our program with a talk by Norbert Werner, who is a professor of theoretical physics and astrophysics here at Masaryk University in Brno. Norbert studies black holes and galaxy clusters, and he thinks that we don't need large and expensive telescopes to observe these objects. He actually thinks that we can study them using small satellites, and that you can build those satellites here in Brno, and hopefully he will tell us a little bit about that in his talk. Norbert's journey to Brno was quite long and winding. He was born in Slovakia, and he has a degree in astrophysics from the Pavol Josef Šafařík University in Košice. He then did his PhD at the University of Utrecht in the Netherlands, and subsequently he spent 8 years at the Kavli Institute for Astrophysics and Cosmology at Stanford University in California. He then returned to Central Europe, first to Budapest, and since 2020 he's been a member of Faculty Hill at Masaryk University in Brno. He's also a member of the Science Working Group of the European Space Agency's Athena mission, which will study high-energy phenomena in the universe, such as X-ray radiation emitted from black holes and galaxy clusters. The mission is scheduled to launch in 2035, and its goal is to understand how these mind-boggling objects form and grow. So, hi Norbert, and thank you for joining us. Before I give you the floor, I just want to ask you a couple of questions, maybe just we can move a little bit in the middle of the stage. So, you had this really complicated journey from Slovakia to the Netherlands to the US. What made you come back?
It's about coming home. I always wanted to come back to my home region. So, and Brno offered the best opportunity in this home region. And I love Brno, so I'm glad to be here.
Still, I would be interested in your point of view, because, I mean, Stanford University, that's one of the really top universities in the world. It ranks in the absolute top 3, I think, with MIT. So coming to like a much smaller place, what would you kind of recommend Czech universities, perhaps some lessons that you've learned from the American experience, maybe that they could implement here to perhaps become a little bit more globally competitive?
Yeah, this is a really hard question. And the only thing that I can say is just kind of an attitude. So, you know, I was at Stanford, which is in the Silicon Valley, and people are there all very optimistic and very, you know, they dare to dream big and then take their dreams serious and then follow their dreams. And I think this gives you a lot of energy. So daring to dream big and then following those dreams is, I think, really important, and it can take us some way.
Fantastic. Thank you very much, and the floor is yours.
Thank you. And thank you for the opportunity to tell you about my views about the ongoing democratization of space activities, in particular space astronomy. So I wouldn't say that we won't need big telescopes. We always will need big multi-billion-dollar observatories like the James Webb Space Telescope, because astronomers, they need to collect photons, and to collect photons you need to build big telescopes. So these instruments will always be needed. But I will argue that there are many big questions in science, in astrophysics, that do not require multi-billion-dollar space observatories, but they can be done even with CubeSats, constellations, in particular constellations of CubeSats, and then there is a really large room to make breakthrough discoveries with so-called microsatellites or small satellites with a weight of about the order of 100 kilograms. So when you think about space astronomy, when you hear space telescope, you, of course, I believe you think Hubble Space Telescope. Hubble Space Telescope provided a really large step forward in astronomy. And this iconic image the Hubble Ultra Deep Field, I think this still touches people when they look at it. This image took Hubble Space Telescope several weeks to take this image. On this image that covers a seemingly empty spot on the sky, a spot on the sky, the area of which is 100 times smaller than the area covered by the full moon, on this image we see 10,000 galaxies. And some of these galaxies are close to the edge of the observable universe. Some of these galaxies that we see on this image, we see them as they were only 500 million years after the Big Bang. Now, with the James Webb Space Telescope, it took only 12 hours to take this image. And on this image, we see now the record holders, the farthest galaxies at really the edge of the observable universe. Galaxies, we see some galaxies as they were only 300 million years after the Big Bang. And to take this image only took 12 hours. This kind of science really does require big observatories, and big observatories working in different wavelengths. My research group works mostly with instruments like the Chandra X-ray Observatory and European XMM Newton. And yes, we are looking forward to the Athena X-ray Observatory that will hopefully fly in 2030s. Now, when we look at the Hubble Deep Field, we see many galaxies. We see the light from the stars in these galaxies. When we image the same area of the sky with the Chandra Space Observatory, we see this. Those stars that we see with Hubble, they don't emit many X-rays. What we see here, we see the vicinity of supermassive black holes of the galaxies that you saw in the previous image. And I think this is amazing. We see X-ray emission that is powered by the matter falling into supermassive black holes in the centers of galaxies. Now, with my research group, we mostly work on the large-scale structure of the universe, on clusters of galaxies like you see on this image. And in particular, we work on studying the hot gas that fills the space between these galaxies. And it is really important to understand the physics of this hot gas, because it turns out that the universe was not very efficient in forming stars. Only about 10% of the normal ordinary matter is locked up in stars. The rest is in the form of very low density gas that fills the space between the galaxies. And we are trying to understand why is it so? Why does this gas not form stars? What are the properties of the 90% of the ordinary matter in the universe? It's important to understand it if we want to understand the evolution of the universe. So currently, this research is being done mostly with these big, expensive space observatories, which will always be needed, and that's why we have the European Space Agency to actually build such multi-billion-dollar observatories. But as I said, there are science areas where we can do breakthrough discoveries also with small missions. And my vision is that in the future, every astronomy department will be able to have a capable space observatory. Now, maybe this statement sounds bold, but I believe that it is true. All this democratization of space activities basically started with CubeSats. As most of you know, in 1999, California Polytechnic University, together with Stanford University, they proposed the so-called CubeSat standard. The goal was to provide students with opportunity to build something with their own hand on a short time scale, to launch it to space, to operate it in space, to gain this hands-on experience. And these CubeSats, they can be launched from the International Space Station, as you can see on this image, or there are many shared launch opportunities today to launch CubeSats. Actually, in the first decade of the 21st century, there were not many CubeSats, but since about 10 years ago, every year there are of the order of at least 100 CubeSats launched. At the beginning, they were small projects by students and enthusiasts. Then in the next stage, CubeSats became a really important tool to demonstrate new technologies for space applications. And then the third epoch where we are getting now is breakthrough science and full-scale commercial use of CubeSats. Interestingly, over 80% of CubeSats were built by private companies and universities. About 50% by private companies and 30% by universities. Only 4% of the launched CubeSats were built by space agencies. So, space agencies don't build many CubeSats, it seems. And so these nanosatellites, they really mean an ongoing revolution in space. And it is driven by standardization, which results in reduction of cost and time, use of off-the-shelf components, flight-proven off-the-shelf components, which again results in cost and time reduction. And then importantly, universities and research groups can work as integrators, which may provide cost reduction, but it provides also training of new professionals who can then be active both in academia and in industry. And it results in spin-offs and startups. So there is this cross-fertilization between universities, research institutes, and small and medium businesses. Then CubeSats can be used now when we come to science for multi-point measurements. So they allow measurements which are not achievable with monolithic systems, with big satellites. So one example is global and high-frequency monitoring of cosmic transients. So I will talk more about this. So when you have explosions in space, like gamma ray bursts, you want to cover the whole sky, and you want to cover the whole sky continuously. This is something you can do with CubeSat constellations, but not with big satellites. And in the same time, you can study the space weather in the Sun-Earth system. Distributed architectures also provide reduction in risk and a drastic reduction in size and mass, which means cost and development time. And you can build up your constellation, your mission, step by step, which reduces risk and increases performance. So you can fully test your hardware and software on a flying satellite in orbit while preparing for the next launch or next launches. So when you draw out the parameter space of development time, cost, risk, performance, global and or high frequency monitoring, then distributed architectures provide you this. They provide you really good performance in global and or high frequency monitoring. The development time is short, cost is low, and risk is low. Now when you look at monolithic systems, they perform well in performance, but not really in these others. So present breakthrough distributed architectures of nanosats and constellations. In astrophysics, events that are really good to study using nanosatellites are gamma ray bursts, because they are bright. Gamma ray bursts can be produced by the gravitational collapse of massive stars, stars that were initially more than 25 times more massive than the Sun, and they turn into black holes. And when they turn into black holes, they produce jets. And if the jet points towards the Earth, then you can see these gamma ray bursts even from the edge of the observable universe. And mergers of neutron stars. Mergers of neutron stars also produce gamma ray bursts. And mergers of neutron stars, as we will see later, they also produce elements, some of the heaviest elements in the universe, elements like iron, platinum, or also uranium. So a mission that we proposed a couple of years ago is called Camelot, CubeSat array for measuring and localizing transients. And the idea is that when we have 10 to 20 CubeSats distributed uniformly on the sky, then we provide all sky coverage, which big satellites do not provide. And we can provide a timing, 0.1 millisecond timing, which allows us to determine the time difference on each satellite when each satellite detected the gamma ray burst. And from that, you can triangulate a position in the sky where this gamma ray burst happened, and this enables follow-up observations from the ground. And to start, we first developed the detector, the gamma ray burst detector. And the in-flight demonstration of this gamma ray burst detector happened on 2 satellites, on GRB Alpha, that was launched in March 2021, so last year, and on VESETELUSAT-2, which was launched in January this year. And these both satellites are performing very well in orbit. So GRB Alpha detected its first gamma ray burst last summer. Here we see one gamma ray burst that is where the gamma rays, the photons, they traveled for 10 billion years across the universe until the time until they hit our detector. So we see something really towards the edge of the observable universe. And you see another gamma ray burst that is from a merger of 2 neutron stars. And here we see 2 gamma ray bursts that GRB Alpha detected less than 24 hours from each other. So the current state is GRB Alpha until today detected 26 transients, 16 long gamma ray bursts, 3 short gamma ray bursts, 5 solar flares, and 2 so-called soft gamma ray repeater events. I'm not going to tell you now what that means, but it's also interesting, neutron stars. And VESETELUSAT-2 detected 14 transients. So after a software update on GRB Alpha that was performed in August, GRB Alpha is now detecting a gamma ray burst every week, practically now maybe every 5 days. Both satellites continue to also monitor the particle environment, the space weather in low Earth orbit. And they have innovative silicon detectors. And actually, one of the goals when we launched it was to learn how they degrade in space. And the good news is they don't degrade much. GRB Alpha is still very sensitive. So these are CubeSats, but as this image illustrates, these days, much heavier satellites are being launched to space in bulk. Here you see the Starlinks, 60 Starlinks packed into the fairing of a Falcon 9. And the development is now going from CubeSats to small sats. This is the trend. And one can do much more with this of the order of 100 kilogram small sats or microsatellites than with CubeSats. And a project that we just proposed in response to a call for an ambitious Czech technology science mission is QVIC, which stands for Quick Ultraviolet Kilonova Surveyor. So what we are proposing is a UV space telescope with a collecting area of 200 square centimeters. This actually means a primary mirror with a diameter of 37 centimeters. And the whole satellite is like 60 times 1 centimeters times 100 centimeter, and the mass is around 100 kilograms right now. The primary objective is detecting and observing kilonovae out to a distance of 200 megaparsec, which means about 500 million light years. This is the distance where these neutron star mergers are also will be detected at that time with the gravitational wave observatories. The goal is to observe this kilonova really early. So far, only 1 kilonova was observed in enough detail, but only after 11-15 hours. And we want to observe it ideally less than 1 hour from the merger of neutron stars. And therefore, the satellite shall have a moderately fast repointing capability. to be able to start observing less than 1 hour after. We need to tell the satellite that please turn there, and we have to be able to tell it to the satellite real time, and therefore the satellite shall have a near real-time communication system. And of course, we will come to the many secondary science objectives. So this is really ambitious, and the prime is vezetelu. We at Masaryk University are responsible for science. TopTech is responsible for developing the telescope, and PKSat for the communication. So what we really need to observe, we need to observe in UV a kilonova very, very early. This tells us about how kilonovae explode, and it tells us about the nucleosynthesis by kilonovae, about the origin of the heaviest elements in the universe, about the origin of elements like gold, platinum, or uranium. So this is our primary mission objective. But actually, in 1 year, it is really uncertain how many kilonovae will we see. The lowest estimate is that we will see a few, and the highest estimate is that we will see a kilonova every week. This is something we just don't know today. But this telescope will be able to do so many other things and to serve the Czech and also the international astronomy community. This telescope will be able to observe follow-up gamma ray burst, supernovae, novae, so this transient phenomena. But also it will be able to observe the transits of exoplanets. It will be able to see how supermassive black holes tear apart stars in galactic centers. So lots of really exciting science, and we are going to provide 50% of the cubic observing time to the international astronomical community to just apply. So I'm towards the end of my time, so I will just summarize here the main conclusions. We are in the midst of a revolution in space technology, and we should take advantage of it. I think everybody in this room agrees. Space is becoming more accessible, so there is opportunity for a bigger variety of experiments and shorter development cycles. So while I believe that while ESA shall support the big missions, which nobody can do alone, and billion or multi-billion dollar class missions, there are missions that can be done also on national level, the smaller missions. And there is a rapid growth in capabilities expected in the next decade, thanks to commercial development, potentially enabling more ambitious missions in terms of weight, data rate, onboard computing, etc. Thank you very much for your attention.
Thank you. And I'm wondering whether perhaps anybody has a question for Norbert in the audience. Okay, if nobody has a question, I have one. I'm curious whether with those satellites that you have right now in orbit, whether you were able to see there was this record-breaking gamma ray burst a couple of months ago, and if you saw it, how your data compares to, let's say, what the big telescopes such as Chandra or Integral see?
Yeah, thank you very much for this question. Yes, we saw this really bright gamma ray burst with GRB alpha. And actually, it was very nice. My colleague Jakub Žipa, who is analyzing data, is just here. He was immediately contacted by colleagues from NASA because Fermi also detected this gamma ray burst, but it was saturated. But our detector is smaller, and we have some innovative technology with the silicon PM detectors, and our detector was not saturated. So there is a chance that we actually can provide those data that what was the peak luminosity of this gamma ray burst.
Wow, so that's something for us to look forward to, and hopefully we will see some papers published about that.
Yes.
Fantastic. Thank you very much for your time. Thank you for being here with us. And we are going to move... Oh, we have a question. Okay.
If you could tell us about the planet orbital parameters of the cubic mission.
Orbital parameters. Yeah. So it's a sun-synchronous orbit, and it's a dawn-dusk orbit, which gives thermal stability, and that seems to be the best option for us.
And it's still like in a low Earth orbit.
Yes, 550 kilometers dawn dusk.
Yeah, thank you.
Thank you for being here with us, and we will now have to move to the next segment of our program. So last week at the Ministerial Council in Paris, the European Space Agency didn't only approve the new class of astronauts, but also a record 17 billion euro budget. And this budget will cover the agency's activities for the next 3 years. If I'm not mistaken, the Czech Republic will contribute about 180 million euros into this budget over the next 3 years, which is 5% more than it contributed in the previous period. And as you surely know, the European Space Agency operates something that is called a geo-return, which means that member states are meant to get back what they invested in the value of ESA contract. So thanks to this contribution of the Czech government, all of you here will be able to pitch and compete for some really interesting European Space Agency projects, such as the Secure Connectivity Constellation IRIS-2, perhaps the Argonaut lunar lander, maybe some of the missing components of the ExoMars rover, which had to be checked out because of the war in Russia, and some of the really exciting science missions like Athena, Ariel, the Comet Interceptor, and many others. So in the next panel, we will talk with some of the people who may be the benefactors of this cooperation and who are the representatives of academia and businesses who are helping to turn these investments into some benefits for the Czech Republic. I hope we have enough chairs here. So let me start. Our first guest will be Professor René Hudec from the Department of Radio Electronics at the Faculty of Electrical Engineering at the Czech Technical University in Prague. Do we have Professor Hudec with us? So Professor Hudec also works with the Institute of Astronomy of the Czech Academy of Sciences, where he focuses on high-energy astrophysics. He has a long history of collaboration on ESA's science space telescopes, including Integral, Gaia, and Athena, and he will also tell us about his experience connecting academia and the commercial sector. Next, we should have Mr. Marian Pícha from the Ministry of Industry and Trade, who will represent the government side of things. Thank you for joining us. Take a chair, please. And next we have Luděk Kier, who is a senior expert at research and consultancy firm Bisgarden, and he is also a member of the board at the Brno Space Cluster. Bisgarden led 2 projects financed by ESA as part of the application promotion program. Spin-offs from these projects were successfully introduced into the market, and Bisgarden also supports new startups entering the downstream space sector. Thank you for joining us today. Then we have Pavel Pořízka, who is the head of the Laser Spectroscopy Laboratory at the Central European Institute of Technology in Brno, and associate professor of mechanical engineering at the University of Technology, Brno. He is also a founder of Lightigo, a company that builds high-tech spectroscopes, which are the types of machines that could perhaps one day find life on Mars. So thank you for joining us. And our final panelist is Martin Kubíček, who is the CEO of Optimi, a Brno-based startup developing tools for engineering simulations and data analysis. The technology that is at the core of Optimi's business is a spin-off from Martin's PhD research, which he conducted at the University of Strathclyde in Glasgow, Scotland. Hello, and take a seat, and thank you for joining us. So we actually have a lot of chairs. This is all I have, but if we have another speaker who was supposed to join us, then we have a spare chair, so please come. It's fine. I'm sorry, I apologize, I wasn't informed. So can we get the chair back?
Mr. Suchanek is quite important person.
Okay, could you introduce him, please? We have a miscommunication here, I apologize.
We collaborate together in education and sharing students and so on. So.
Great. And maybe because some of you are perhaps better known than others, I would perhaps just start asking each of you just to briefly introduce yourself and explain your involvement with the space sector. Perhaps we could start with Professor
I am professor for space engineering, so teaching students approximately 35, something like it. I have 6 PhD students working in space business, and I started already maybe 5-10 years ago to collaborate with space companies which are in the Czech Republic to share students. In the sense, we are looking for collaborative thesis, semestral works, dissertations between university and company for the students. It is very good because they can work in space business, they can learn technologies and so on. And for companies it is again very good because they can select good students for future involvement in space projects with these companies.
Fantastic, thank you. So, Mr. Piecha, could you just few words?
Well, hello to you all. I'm quite new to this space, but I came here to learn. I work at the Ministry of Industry and Trade. I'm a deputy minister responsible for all the EU money, all the operational programs connected with entrepreneurship and business development, or operational program technology and application for competitiveness. And then in my portfolio is Recovery Resilience Fund, also known as Národní plán obnovy. Thank you.
Thank you. Mr. Kier.
Yeah, I'm probably the crazy bird here in the group. Mostly when you've been talking here in previous speeches, I didn't understand anything, because I'm really just doing my business, using crazy ideas to develop some applications on Earth using space technologies. We have done it since we've been established in 2010, so 12 years already. We've led some ESA projects, especially in the program, this application promotion program, because ESA is sending, and the European Commission is financing a lot of technologies, satellites, equipments which are circulating the Earth, and we should use them on the Earth for some business or some services from which the people benefit on the Earth. So this is our business.
Thank you. Mr. Božiska, could you tell us a few words?
Yeah, just very briefly, we are working at the university doing optical emission spectroscopy and especially laser ablation-based spectroscopy, which is quite interesting also in terms of Mars rovers and other extraterrestrial analysis. And currently, we are just moving from the university as we have established a startup company, Lightigo, and we also see the opportunity in space. So therefore, we have established also a subsidiary, Lightigo Space, for this reason. And just to mention our involvement, we are now working with Sub Aerospace and other companies and institutions on Slavia mission. And also we are working on international basis, working with companies or even universities involved in NASA research of Mars and the ChemChem and SuperChem team. So we are now just trying to be there as well. So this is the opportunity for us in this sense.
Thank you. Martin, would you like to introduce
Hello,
your company?
my name is Martin Kubíček and I'm CEO and head of the company Optimi. We focus on data analytics for engineering processes and basically using AI to improve the designs in engineering departments. Our involvement in space is a little bit broader because we started as an incubator in European Space Business Incubation Center here in Prague. And currently we get a contract from ESA on development of a new type of holder for a thruster. And this is done in cooperation with AVO.
Thank you very much. And Mr. Suchanek.
So, hello, good afternoon. My name is Petr Suchanek and I'm from ESE Aerospace. The involvement of this company in the space domain is quite wide. We have been involved in many software projects, many, let's say, test activities. Now we are also involved in electronics for space missions. And here I would mention very briefly the Space Rider, which I think for the next ESA, next 3 years of ESA funding, this would be a very important project. I'm here also to support the idea of having students as good team members, offering some bachelor thesis or topics to them, perhaps leading to diploma thesis, and eventually offering, let's say, engagement in normal projects as such. So I presume that it would be the discussion afterwards.
Thank you very much. I would like to get a little bit current, but if you're not comfortable with the question, you don't need to answer. But I mentioned previously that the ESA Ministerial Council approved this record-breaking budget, 17% higher than its previous budget. The Czech contribution was also record-breaking, 5% higher, but still the Czech contribution only makes up about 1% of the ESA budget. And I wonder, from your perspective, being such a small country, even with this increased investment, still quite a small player, how does it affect or limit the opportunities of Czech academics and businesses? And how can you go about that? Anybody feels like answering this question?
Maybe I will start. So, you know, we are at the university, so we learned already to work with very little money. But still, I believe that the students which are involved, especially PhD students, they need at least some good stipends and so on for participation in projects. So we hope for a better future, yeah. But on the other hand, working with students like bachelor and diploma students, then really having very good students, we can make a very good job with very little money. We need hardware, yeah, but this labor work is very, very small, yeah. So, but it is from the view of university. I know that for a company it is impossible to work for little money, yeah. So.
I can just. I was a little involved in a few years ago when the Czech space program was developed, and I know that the ministry is always thinking or measuring the opportunity to invest in the ESA on the capacities of Czech industries. So I don't think that it's not enough. It is enough. There are other sources. Horizon is offering money. OSPA is offering money. Yesterday I've seen a map that the Czech projects in EUSPA there are 11 Czech projects, 36 from Germany. So I don't think that there is not enough money. The limits are in our heads. We've been a small company, knowing nothing about space, and we came with some ideas how to use space technologies on the Earth. And we managed to have 2 big projects with ESA, always starting with a study, then with a demonstration project, and now we have, from these 2 projects, one is still running, we are now finishing it. It was the first project co-financed by ESA and EDA, European Defense Agency. The previous one was fully focused on tourism and information and services in mountain resorts. And from these projects, there are still 3 products, or there are 3 products on the market. Spin-offs, technologies involved in services, saving lives on the mountains. So it's, I think it's measured on Czech capacity, it's enough, and I'm grateful to your Czech ministries that they still see space industry as a with a very high potential, even in the time when all budgets are cut. Yeah, we have to see also these bigger picture of the time in which we are now living. Yeah, so I'm pretty sure it's good.
Thank you, Mr. Bek.
Well, it's quite a tricky question, because if I will go to Czech politics about the basic applied research and where the money should go from the technology agency, where the money is put from the structural funds, there will be a very long discussion. So maybe I will start on the European level. Definitely, we just today finished the big conference for support of SMEs and how to go with the SME relief package and where to put the money in. And on the European level, I think, like a lot of politicians present, that green and digital is the way. That all the projects needs to be green and digital. Okay, now they are a little bit moving from green to sustainable and circular economy, which is great because then you can really see what's inside of the projects. All the projects can be green, and especially for Czech, Central and Eastern Europe now, I think the whole automotive industry, it's just a little bit overheated. Even now in Slovakia there will be another Volvo company, and we are too much focused on automotive. And then again, even Europe going green and digital is promoting this kind of industries, because the car engine can also be each year greener and digital, even though it's 120 years old. And this is what actually the car manufacturers persuaded the European Commission to go in this direction, because every year you can get more digital, more green car. But what about the pharmaceuticals? What about the fighting cancer? What about the space industry? Well, just if I look in the programs which are developed under the European Commission, under the RRF or the structural funds, I see that this green in digital is a little bit killing the substance of some other industries like space, because after all, you can be very digital, but you don't really you can be sustainable, but then again you are competing with the car manufacturers. And I think going back on the Czech level, we need to really distribute what are the potential, what is the potential for the Czech industries, what we should support from the state budget, because then there we have more freedom. I'm always saying that we should look at the countries like United Kingdom and so on, where they have a special national programs for, I would not even say space, but general aircraft making industry. And they support the whole aviation as a part of industry. They support the pharmaceutics as something which I would call the golden egg, the golden part of the whole industry. And then from structural funds and everything else, we can support the regional development. In R&D, we can support all what needs to be green and what needs to be digital, because there is not really a time to persuade all the Commission, everyone, that there are some other topics we need to create them on the national level. That's why actually I'm very happy to be here, because with all the space weeks happening in Prague, in Brno, and all over the country, I think we are getting noticed. So this is the good thing from the point of view of how much money should be devoted on this topic. But I would say we need to solve it on the national level first.
Thank you. Anybody else would like to comment on this?
Maybe I will try a little bit. Actually, I would take it from the point of view that do not see it as an obstacle that we have a limited budget in ESA, and it's actually lower than the increase generally. I would take it as a guidance for a way which we should go. To give an example, with this kind of a budget, we cannot build a company which will compete with Airbus, right? Because simply there is not enough money. And how to overcome it? Well, basically come with innovative ideas. So this is telling us that our way of approaching business, or our way of future development, is to bring innovative people and innovative companies in the Czech industry, in the Czech environment. And hence, with this money, we should understand that these innovations are very risky, and this is for gentlemen from our government to understand it as well. And hence, they allow innovative people to build new stuff, and our government and gentlemen from government, sorry, to say it this way, will take the risk, will say, okay, we will try it. So, as I said, I do not see it as an obstacle, I see it as a way how to create new things. And also, I should add that these innovative businesses will sustain even in the case of crisis, which are repeatedly coming over a certain period of years, right? Because this is the nature of the environment. So I hope this answers enough.
Thank you. Anybody else? Mr. Pořízka is nodding, so I was wondering whether you have something to add.
Maybe just very briefly, because we have just spent a lot of time about this topic, but statistically speaking, I believe that always we think that, or just we hope that there will be increase, and that the increase keeps pace with the growth of the industry, and I believe it will be sufficient. But taking into account other countries, like statistically speaking, the Denmark and Finland are having the same share of this, just around 1%, and when just considering the increase of the funding, we are a bit behind of Austria and Poland. So just looking around our neighbors, so this is something that I think we are just really on some similar level in this sense. Yeah.
Thank you. So Mr. Suchanek would like to add.
So it is also a matter of how the budget is distributed, because in ESA there are multiple programs, and for example, Earth observation, or which is long term, it is here basically since the beginning, and in recent, let's speak for example about cybersecurity. So if we shall judge how the money, whether the increase is interesting, let's rather discuss how it is distributed. I don't know the exact numbers, but in my opinion, this is a better question.
Are you happy with how it's distributed?
For us, yes.
Thank you. So let's move to the next topic. When we talk about space and new space especially, we always talk about startups, these kind of highly innovative new companies. And there is always a lot of challenges with these companies. Many startups are founded and a lot of them die along the way. And we also always hear about the differences between the US, where there is much more venture capital, much more funding to go about compared to Europe, Europe being more risk averse. So I'm curious, because there are a few of you who have these small innovative companies, what specific challenges do you see starting such companies in the Czech Republic? And what sort of support are you getting, and is that enough?
Okay, so I should start? Okay. Actually, the point is that it's not about funding. Here in Czech Republic, we are very conservative, and somehow I was told that one person, the boss, should be capable of doing everything. Contrary, in the US, for example, and with my friends and colleagues in US, they understand that building the team is the key, because one person cannot handle everything, right? And this is, for example, what I'm missing on our universities, that we have brilliant technicians, like literally brilliant, and I can say that because I was working with people from Caltech, from Stanford, from Cambridge, etc., etc. And I specifically named these famous names, right? And all the time they were coming to me for an ideas, and I was thinking like, why they are coming from me? I'm just from the middle of Czech Republic, from Brno, which nobody knows where it is, on the west, right? So, as I was saying, what we rather need is to teach young people and young entrepreneurs how to build and create a team and how to maintain it. This was the key point from my company, that I learned how to trust my colleagues, how to assign them to a proper job, and how to get results from them. So this is the key for startups, and this is from my point of view why many of these startups fail, that we don't know how to build properly the team which are capable to deliver the task.
Maybe I'll just stay with you for a moment, because I know that you studied at Strathclyde University, that's in Glasgow. There's this big space cluster, and yet you came back to Brno to start your company. So I just wonder, why did you choose to come back to the Czech Republic to do that?
Well, first, Czech Republic is my home country, right? So this was one of the main reasons. Secondary, I was in Scotland, even if the connection to the space sector is really is much bigger than here in Czech Republic. Actually, Strathclyde is one of the biggest universities which supplies the people to the ESA, right? I have a lot of friends there, actually, who are working right now there. But the point was that I knew this environment, I feel home here, and I saw the potential in the people here. I knew that when I will go to the Brno University of Technology and ask my colleagues if they want to join me, I know that I'm getting one of the best people in the world. So this was one of the main reasons why I came back to Czech Republic to start the business here. And also, I should also mention people from Incubation Center here in Prague. When I was in the discussion with them, they were very helpful. And basically they helped me to establish the business here. Because it may sound crazy, but when I started the business, I didn't even know that there exists something like invoice. You know, as I said, I was specialized in one particular field, and I didn't know about anything else. And in this incubation center, they helped me to understand the other fields as well. And also they helped me to understand how important is to create a team, as I was saying before.
Thank you. Pavel Božiska.
Yeah, I maybe will continue on what has been already said, and I think that there is actually good opportunity in Brno, and the ecosystem here for small companies is really improving and significantly improved. I have just maybe limited experience. I'm here in the company and some companies and transfer of technology for 8 years. But for those 8 years, it significantly improved. From some rough beginnings, also on our side, understanding and just completely changing the mindset from just, being some research-driven ideas, oh, this is nice, we do it, so everyone has to like it and buy it from us, to completely change the mindset and perspective demand, like the market-driven demand. And this was just really the understanding of this was helped by the South Moravian region, this innovation center, and also our technology transfer office, and so on. So there are a lot of people involved in here right now, and I think this is supporting the startups. And once you understand this, or just we have also had to understand it, and it was a process. It took us some time, so I think now we are just more involved, and just it's more straightforward for us right now. And also there is also support from the cluster right now, which is doing a really good job, I believe, to just really compile all those companies, establish some value chain, and just say okay, there are multiple companies that are involved in different things, and it helps us to cooperate together and move faster forward. Especially, as I said, for us, SAP Aerospace was a big boost in this matter to establish us.
I have one more question for you. So you said you are involved in some NASA kind of projects. How difficult was it to get this cooperation?
We are on external. We are working with German university and a Spanish university, which are directly involved with the Superchem team, and it's extremely difficult. Like the Roger Wiens, who is the leader of the Chemchem and Superchem team, is like a rock star in the community. So everyone wants to be with him. So for us, we are just really step by step getting closer. And for us, we have a really strong connection with German and a Spanish team, which is directly involved there. So for us, it's indirect, but we are working on some data processing and basic research and laser ablation systems that we help. And we have multiple students going to Spain and Germany as well. So this is our involvement, and we are just really moving forward to this as well, I hope.
Thank you. I would move to the next question, and that is, do you think there is a sufficient ecosystem for spinning university research into companies? I wonder, perhaps Professor Hudec may have something.
This is difficult to say because we usually work with bigger companies, but we also have some experience with 3-4 this spin-off company, young. But I have to say some are very good, or the people are very good, but some disappear in 2 or 3 years, which is not very good. I know in Prague it's a big, they do a very perfect job, but it is the same problem. The companies are very good, they are created, and then maybe 50% they disappear later. I would say I like your idea. The innovation is the key. Because we need good ideas, and this is related really to young people, because when I allocate some student work, thesis or something like it, I am always happy when the student is coming and saying, I have a new idea, because this is absolutely perfect. On the other side, on big satellite projects of ESA, NASA, this is very difficult to put into the orbit something really new, because they want everything to have something which is reliable, space qualified for a couple of years. We have personal experience with this lobster eye technology. We have very difficult to place on satellite because it is new technology, never flown into space. So it is a little bit trade-off, not so easy, but a good idea to work in the direction innovation.
Well, if I may a little bit go back even to the first question, I think the good thing in Czech is that we have infrastructure working. I think the Brno is one of the great examples that all the creation of the business incubators, technological parks as an infrastructure for the spin-off and business promotion worked well. And now we need to go step by step. I think what is most important is really to work on the academia with the demand coming from the companies. Because there you see a really commercial potential. That's why we are so fond, and the Ministry of Industry of the program application, where we promote the entrepreneurs, small and medium and large companies, to go and ask to collaborate on the research with universities. And from this closer cooperation, then the spin-off can really make sense, because in substitutes the production for the bigger company or smaller company, and it has potential from the beginning. Of course, there's other way, like all of the researchers want to aim for the Nobel Prize and having the research something which will be paid off billions of dollars. And I'm always surprised, like in Czech, and I would say it works for the space industry the best, that we can be really in some parts very, very, very good climbing the Mount Everest, and we can really do it like to be the best, and then create a spin-off there. But generally around our academia and potential of the universities and potential of the industry, I would go rather for innovations and really driven the research by innovation, real low, just everyone on easy level, first hiking the Sněžka, then go to different mountains, and finally we'll be all climbing the Mount Everest. Thank you.
Maybe if I may, I will just add, exactly we were saying it's difficult to get to the big satellites and this stuff, but every unique idea and every business which can be another Škoda starts like this, that you, as you mentioned, start climbing by small steps, and well, you must hope, every step you hope, but in the end there will be another Škoda, and it will be focused on a space business.
I think it's very much connected with the previous question. The entrepreneurial spirit in Czech Republic, I miss it a little when I compare it with countries like Estonia or Poland, because one of our spin-offs of one of our space projects is in Poland, and I see the drive there. Of course, they make a lot of mistakes and very often failures, but the culture of failure is missing here. Everybody is just afraid. Okay, we do it, but we can get bankrupt. Fuck off. Try it. Go for it, because otherwise you will always sit on your old chair doing some research, never coming to the market. For some people it's great because they do not have this spirit of making failures, going for the risk. But you know, some years ago there was a kind of wave, like even influencers, ladies influencers have written in their posts, I didn't have yet a startupper. That's crazy, I have to get one. It's over. We do not hear anything about startups here. Just in a very special environments we are talking about startups, but it's not so frequently on the news, it's not frequently discussed on TV, it's never, I can't see anything right now. So, and one of the systems, the lean startup, says it's like invent, design, try out, fail, redesign, try, fail, and maybe in the third round you are successful. And we fear the failure so much that we even do not try. And that's a big problem of Czech Republic. And it starts with the education. I think at the grammar school, at the schools, the high schools, just getting a note 1, 2, 3, 4, 5. Why? Okay, I've got a 5, but I'm good in other things, or it was my failure this time, next time it can be much better. So it's the fear of failure is something that blocks us from being successful and going for the next step. And I've seen yesterday a nice picture, which was a guy was explaining that 10% of his life is determined by things which happen, and 90% is determined by how he reacts on these things. So if you react well on a failure, it can bring you further forward. And that's what's missing here, I think. We have to work on that every day.
Martin Kubicek.
Maybe I will add one very interesting point. You just mentioned universities and not business and innovative driven. And actually, this resonates me very strongly because when I was sitting behind the desk, you know, and listening to the teacher, he was saying, when you will be employed, you will do this, this, this. Why not to change it to a sentence, when you will have your own business, you will do this. And start changing their mentality from employer to a business person.
I think it's great that you got to the education, because I was actually wanting to ask you, do you see sufficient demand of young people going into the disciplines, and is there a sufficient, let's say, talent funnel for the space industries, or do you think that's something that needs to be improved? Professor Ritz.
I would say that at least the students they are very motivated because you know already astronomy, astrophysics, we have very good background in population, in the community, because many people are, for example, amateur astronomers. So many students are coming from outside because they like space, they like astronomy, astrophysics, they like satellite, and having such motivation is very important. Maybe this is even more important than funding, but funding is also important, so we need both, yeah, I would say.
So would you say there is enough talent coming into the academia?
Talent is not enough. You know, talent is important, but you need motivation. If the student is motivated, if I allocate topics for thesis diploma, which is perfectly fitting the interest of the students, the students will provide maximum. Yeah.
But would you say it's enough people coming?
No.
It depends. Not. Enough good people. We need excellent, good students. And I am sure you will agree, for your companies you need also clever and very good people.
Actually, yes. I mean, the general answer to this one, there is not enough clever and excellent people anytime, anywhere, right? Yeah, I fully agree on this one that we need to get these people more often better.
I have to only I will be very short. About 6 years ago, I got a phone call from one colleague in Switzerland, in Geneva, and he asked me, please send one of 2 students, but please send very good, excellent students. Don't send bad students, because we already have many.
I think there was, yeah, go on.
I can contribute to this, that the companies themselves have to try to help this educational process probably, because at the universities you cannot gather all the information which will eventually be needed. So we can have students who can design circuitry, whatever, software.
The academia, in order to help the academia understand what the industry needs in the graduates.
I think this could be improved, this is for sure. For this to help, we are also trying to, at the Czech Technical University, to support some educational lectures. So we have at least one. I think it is every year, so one lecture per year. It is not enough, but it's at least something. But it is what we are trying to teach there. It is more about procedure of how to fit into a project and how to handle the project management in general. But this has to be improved.
Thank you. I think Pavel Pořízka sort of wanted to add something about the amount of people coming into. You said no when Professor Hudec was speaking, so I was wondering perhaps you would like to add a little bit.
Yeah, I didn't want to be in disagreement with it. It's not. I believe that the quality is really good. It's getting better. But the quantity is really insufficient, and we can see that like the big companies in Brno are consuming a lot of students, and especially for PhD, that the student is just doing master and going for PhD. We have to also motivate the students somehow to stay for PhD, because then they can just really level up in this sense. And yeah, as I say, the number of master students could be also higher. That might be really good.
Well, maybe if I will add, as a former PhD student from foreign university, I fully agree with the project management. That is one of the big issues of Czech universities. And also presenting the results and presenting the idea of the research. I will give you an example of myself. When I finished the university and I was making a presentation about the topic which I do, there are a lot of equations, a lot of very smart things, and the people were bored in like 5 seconds after watching the second slide, okay? Of course, I immediately lose everything after the presentation. Today, when I'm doing presentation, the rule is no equations, mainly in the background, some, improving my ego, or but main focus is just key points and very simple sentences, and highlights only the words, because people will remember these words, and then they will come back and tell me, Martin, your topic looks interesting, let's have a deeper talk about it. And this is what it's about and what is actually missing on Czech universities, from my point of view.
Well, actually, you guys here with the space industry, you have a great potential for attracting students. Like there was a colleague of mine, Mr. Muřický, earlier here today, I believe. So I learned. So you had 2 deputy ministers here at this conference, even though that from the point of view of GDP, it's not really interesting topic. We should rather go to car producer or something. But we are here. We are here because it's a sexy topic. Because everyone, at least I also wanted to be an astronaut, at least a pilot. And so everyone who wants to, just general, just in a kindergarten, preschools, just elementary schools, explaining the potential of space for those kids, even though that 99% of those students will end up on Earth, not going to space, but they will learn what's the mathematics about, they will learn what's the physics about, and they will be able to create the projects which are in the lower parts of the atmosphere. For example, the last week we had entrepreneurial awards on the level of the Czech Ministry of Industry and Trade, and the winner in applied research was the company Metroples. And I was surprised how the team from Prague could build. I'm not sure. I don't want to really use the proper word because you know it and I don't know it, but something which can a radar which come up with the progress of the weather, and they are able to say to sell 11 of them into India, and they are not able to sell one in Czech, but it's completely different story. But the point here is, if you will promote the space and the astronauts and all what you are talking about, we will have a potential of students for even the flight industry able to calculate something and be able to be great in physics. That's why it's so sexy.
Maybe I will slightly disagree on the GDP, because if you will coming with a technology from space and it's successful, the return is 7 times. 7 times like more than what you invested. So in the GDP, I will slightly disagree. Nevertheless, I have something a little bit more important to say. Right now there is a war on Ukraine, right? And what helps the Ukrainian people to stop the invasion from the Russians, right? It's rockets. And this is coming from a space. So the potential of the space research is not only about GDP, it's maybe also about our survival as a society, right? Sorry, I'm overstepping a little bit maybe to a different topic. So, thanks.
Thank you. I would like to give the opportunity to our audience to ask questions, if there is anybody who would like to ask any of our speakers anything. No one? There is a hand.
Ginter Klatečka, thank you very much. I really enjoyed the discussion. Just a short comment about the bad students that I heard. I am trying always to think there is no bad students. There are always like a people who have like a different ideas and, you know, different background. And I think it's always about the motivation. And so I don't believe I think there are only good students.
I think this was directed to me. I didn't say that there are bad students. I said that we need to get them on the level which is needed in the project. Which, if for students who never have seen some big project, it's normal. So it just requires effort.
Effort on our side to motivate them.
Of course, right? Motivate, educate, and let's say train on how to make it.
Maybe I'll just add something. Is it kind of common for Czech universities to send students like for internships during their degrees, or is it something that perhaps would be an answer?
We offer bachelor topics for bachelor thesis, also for diploma thesis, so a short answer would be yes, but I don't want to say that it is common for Czech industry. Mm-hmm. I represent one company only.
There was another question.
Thank you very much. I'm very happy that this discussion is about the potential, because actually this event is about potential of universities to support this area of space education and research and businesses in particular. But what I would like to say that I'm also very happy to hear that apart from money, we should talk about the environment, this ecosystem of for making businesses. And I must say that in our university we try to create a real liberal environment to motivate people to come with their ideas and to implement these ideas to make startups. We innovated significantly the regulations for establishment of these startups so that we could force people. If you have an idea, come and we will support you in some way. Of course, when we seed money are important, and we believe that in case we have ideas, money will come. So, thank you.
Thank you.
I just wanted to react on Peter. Industries can use students, and we are not specialized in space now, but we have also the other part specialized on digitalization in tourism and digital transition in tourism. And we are using students as working force in our office, and I think in the last 6 years, 7 years, thanks to my colleagues' experience and expertise, we have hosted about 200 students, Erasmus students, in our small premises, and it's working well. Yeah? We just needed to develop a system how to choose the right ones, and a system how to use them efficiently for what we need. Yeah. So industries could learn it. We could give you some lessons.
Thank you. Any more questions in the audience over there? The microphone is on its way.
One question which I really did not get an answer, or from what you said. You said, or some of you, that you are quite happy with the amount of money which are coming because we are a small country, etc., etc. Are you serious, or is it kind of, I mean, you try to convince yourself this is like this, or you really look forward, as you are trying to say, that we will be better and better, and you really understand, no, this is complete nonsense. Of course, there is a lack of money, lack of equipment, etc., etc. Or, I mean, I really did not get what some of you were talking about.
Probably it's directed to me, yeah. I'm a little on the side of the ministry, because I've seen, sorry, but I'm not ministerial officer, so I'm private. But I know that they always think about how to put together the capacity of the industry and the space budget. And I'm happy that they are able to increase it nowadays in these times when everything goes down. This is a great job what they have done. Of course, there is never enough money. Yeah? If you have some, give me that money and I will do something with that. But there are other sources. I have an experience from Poland. Poland is completely different in many things. They think a little in the American way. They think a little more like risk-oriented. There are big companies in Poland have to set up funds which are then distributed to innovative projects, to startups. And this is, I think, also a system which makes Poland a little America in Europe, because there we get money, we get seed money for startups in companies which we spin off from our space projects.
I don't want to interrupt you. Yeah. I mean, I think you cannot, and it's wrong to compare at the moment Poland and Czech Republic. If you compare amount of Polish people who are living in UK and USA, it's completely different business. Their connections, etc., are completely different. If you look at the building of army of Poland, it's completely different business if you compare it with Czech Republic. So you are comparing at the moment uncomparable. I was talking about something else. I was talking about you are looking in the future, but you are not talking about future. And it was not about ministry, a criticism of ministry. Ministry is trying to do, let's say, at least some people are trying to do their best. But it is about Czech state and businessmen and people who have some vision. Please, can you show me in Czech Republic some Elon Musk or people like of this? I mean, just yes, this is something what you can discuss, and which companies you see going in this direction, and this should be in a mutual agreement with the state, with Czech Republic, which should go all together to build such environment. And that's all.
Yeah, I see a few persons like that, especially in the Brno space cluster. There are people with this potential. I don't want to name them. I don't want to make marketing for them. But they are that good that they could achieve it. Yeah, they are good in marketing like Elon Musk. They are able to excite people, they are able to gather money and to start big projects. Of course, in the size of Czech Republic compared to the US, for instance, yeah. But these people are there.
If I can return it into the question, just from the statistical point of view, what is the chance that in 10 million of the people here in Czech we will have one Elton mask comparing to the population of the world? There's a very, very small chance. And I'm even from this statistic surprised that we have this type of companies. But generally, much bigger potential for Czech is to have stable, good, demand-driven, innovative companies in aircraft industry generally. But your comment here was right. The money, there will be less money because generally, as we joined the European Union, we had the big support for R&D and the whole development. There was like the previous programming period ending next year was very generous from the point of view of money. We're supporting in the program of application everything what had commercial potential. And we will get less and less money. So we will need to have bigger competition, and the projects will feel it in 5, 6 years. They will say we need more.
So Martin Kubíček, and we will have to wrap up.
Maybe I will add. You are right. There's never enough money. However, let me remind you of a very famous Calhoun experiment, if I remember the name correctly. It was about the mouse. Group of mouse which were put in an environment where they have everything, and they died later on. So from my point of view, it's not about money, it's about the way of the thinking. Because when I realize there is not enough money, I need to find another way. And this another way could be successful. And then this is connected to your way, or your way of thinking, to understand that failure is also something which I should take into consideration and do not be afraid. So what I'm saying is not that I'm afraid there's not enough money. What I'm saying is find another way how to approach the problem.
Thank you very much. Thank you all for your great questions. It was a really engaging discussion. Thank you all here in the panel. Unfortunately, our time is up, and we just have to go into the next coffee break before the final part of our program. So I will see you all back here in 15 minutes. Thank you very much. Thank you. Well. Okay. So, welcome back. We're entering the final section of the official part of our program. In the previous sections, we have heard from Czech universities and research institutes. We have heard from startups and businesses. And now we're going to dive deeper into some of the interesting research that's going on here in Brno. We'll also look at some interesting international collaborations from outside and inside of ESA. The final hour and 15 minutes will have a form of 3 roundtables, and we will try to let you ask questions at the end of each. So let's move to the first topic, which is a Czech collaboration with Taiwan on a new international maritime navigation network. So let me welcome Tomáš Godhans. Do we have Tomáš Godhans here? Who is an associate professor in electronics and communication technology at Brno University of Technology. Thank you for joining us. Next, we have Xavier Liao, who is a senior researcher in space policy and governance and an international consultant on space maritime cross-sector cooperation at the Intelligent Maritime Research Center of the National Taiwan Ocean University in Keelung, Taiwan. That's a bit of a mouthful. Hello, Xavier. Please take a seat. Our third guest is Tomáš Koutník, who is the head of applications at Optimi. Hello, Tomáš. Thank you for joining us. And finally, joining us online should be Shenglong Cao, who is a director at the Intelligent Maritime Research Center at the National Taiwan Ocean University in Keelung, Taiwan. I'm not sure whether we have...
Hello.
Hello, hello. Do we have
Hello,
him?
everyone.
Now we see your slides. Fantastic. And he's also the leader of the Maritime AIS CubeSat program, of which we will learn more very soon. So let's dive right in. And let's start from the beginning. So this network you're working on, could you just tell me a little bit more about it and how is it different from the other maritime satellite networks that exist?
So I first of all have to thank you all for the invitation. Also, I'm very glad and honored to be here. First of all, I would like to say I was the policy advisor for the Taiwan National Space Program. When I strongly introduced that developing space program should be taking care of the industrialization. I think come back to the discussion we have heard today, I feel it's very interesting that Taiwan is an isolated country. So when we develop space program, we don't have ESA, we don't have NASA, we don't have nobody, we are alone. So that's why we try to develop space program that should be applied to the reality. So this is basically the basic idea from the program we are working now, hosted by Intelligent Maritime Research Center of National Taiwan Ocean University, which try to combine the space technology, especially on satellites, to apply on the maritime security, safety, and sustainability applications. So this brings us to looking for international partners and try to build our network. I have to thank Dr. Kubicek from UTIMAT. Thanks to him, he introduced us to know Brno University of Technology. And then we have luckily meet Dr. Salani, that he basically invites me to visit your university and meet very interesting researchers like Dr. Godhans and the other faculty members. So this is we are starting doing this entire program. If I may see my slides.
I'm not sure how this is managed, to be honest. I think we just wanted to have a picture of satellites there, but I'm not sure whether this is happening or not. Because you know what, I think we have a little problem because we have your colleague connected. So,
I think it should be very brief. The entire idea is that we are using the satellite program. The AIS, so the automatic identification system for maritime safety use, that link with the space tech. This will serve, I hope Professor Gao will give you more insights on how we are working on that program in Taiwan. That will serve to, first of all, the offshore wind farm area security and safety. And on top of that, we're working on using this satellite technology to connect it with the VDES system. And that will ensure the security, safety, and sustainability issues. So on one hand, as you may know, that Taiwan has a very big neighbor, so China, just with the Taiwan Strait as a middle line. So whenever we have a navigation or a vessel go through this area, or we are going to install the offshore wind farms, there's a lot of security, safety concerns. And this satellite program can basically assist the entire communication program that will be proceed safely. So this is a general picture of the program. Now we are working also not only with the Brno University of Technology, we're also working with Polish Gdynia Maritime University, Gdańsk University of Technology, with Japan, with some colleagues from JAXA. We are working on the VDES legal issue, because this is also a very important issue. So I have to say this is an interdisciplinary program that we are developing, and we are welcome. We are very happy to have already our international partner to be with us, and we are looking for also the future program. Maybe I will give the floor to the other speakers or to Professor Gao to have more insight on the program.
So I wonder whether perhaps Tomáš Godhans wants to add anything about what makes this constellation unique compared to the other sort of maritime navigation networks that we have.
So good afternoon, everyone. Good afternoon, ladies and gentlemen. I can see many familiar faces, so it is my pleasure to be here. I would like to. Can you hear me? I would like to say that this network is. I think, in my opinion, quite unique because it uses formation of satellites, or it can use formation of satellites, and those satellites are communicating. So the satellites are on low Earth orbit, which could be quite interesting. We can see there are already several satellites communicating on low Earth orbit, like Starlink. So we think this network could be very, very interesting for not only monitoring the maritime networks, but also it can be used for other applications. But I would like to also introduce ourselves, because we already have some experience, as you may know, with communication systems. At our faculty, there is our Professor Casal, our father of what we do, and I think he has over 50 years of experience with communicating with satellites, and we are trying to follow his steps. I think we are still learning, but we are trying to catch. So I think this cooperation could be also very interesting, not only from the let's say technical point of view, but also from the research point of view.
Mm-hmm. I'm not sure whether we've lost Professor Kao, so I'm not sure whether our technical team. Do we hear you, Professor Kao, at all? It seems we have some. This is your slide. Okay, it's a bit confusing. I'm not sure whether we have Professor Kao, but my next question was whether you can sort of describe the constellation, like how many satellites will you need and what type of satellites will they be? So that was supposed to be a question for Professor Kao, but in case he's not with us, then if either of you could take it. Technology, sorry. So would either of you like to answer?
So I can quickly, maybe in place of Professor Gao. So for the moment, there is already one U CubeSat in orbit that was launched a year ago. We are preparing the second CubeSat that will be launched in a year or so. I think come back to what I've learned from today's session, that the first two CubeSat we have developed, or we are developing, we depend heavily on the public funding. But with those experiences, we also learn another thing is that money is never an issue, because this is never enough. So depending on the public funding, on one hand, it's very good. On the other hand, it may be a limit to us. So now we are preparing the third one. I think Professor Gao can probably explain better than I am. So next one will be a 6U CubeSat, and that one should turn to total commercialized, and also together with international partners. The strategy or the idea is that once we can establish the international network on this CubeSat constellation, from the R&D phase, we'll be able to improve each site or all partners' R&D capacity. And meanwhile, we can also test our each product or capacity in each national market. And that means we can penetrate to another national market, because as I repeat once again, Taiwan is only a small island with 35,000 square meters of surface with 23 million people. We depend heavily on exportation. So without the foreign partners, basically none of the industry can survive. As you may know, that the TSMC, now everybody's talking about that. So I think one point is interesting to mention that this program is supported by Taiwanese Industrial Technology Research Institute. This institute is basically a key actor between government and university and research institutes. They themselves do a lot of research. The iTree basically is the cradle for several Taiwanese advanced manufacturing industry like TSMC. So 30 years ago, TSMC, when it was still a startup, is based on the iTree support to nowadays reach the current stage. So now new wind blow to space industry that we hope that they support the entire program to be internationalized and also to be applicable in the domestic market first and also in international markets. And for the timeline, that will be defined in the coming February, because we are inviting our partners to have an expert meeting in February 2023, because the COVID lockdown restriction measures only opened a month ago in Taiwan.
Mm-hmm. I think they should be connecting Professor Kao. Professor Kao, do you hear us?
Yes.
So
yes, I hear you.
Could you tell us a little bit more about the constellation? How is it going to work?
Okay. Let me introduce our constellation for the Taiwan CubeSat ARS and VTEX. As we know, like the members of National Taiwan Ocean University, we are the members of the NAR labs. And then now you can find the story about the CubeSat for the ARS is for the intelligent navigational safety planning for the western Taiwan wind fronts. Also, the ARS, the CubeSat maybe will the application in the wind fronts because of there are a lot of the flying area for the base station in the shore. So you can see this is our maritime satellite history. Now we want to transfer communication network from the satellite communication system and connect it to the base station and the satellite stations. Now is the original, the U-San CubeSat, the first CubeSat satellite in Taiwan. And now we have some presentation and we have some of the papers. And now this is the CubeSat, the original one. It's very small. It's 1.5 U. The purpose is for the purpose is for to modify and monitoring the blind area from the base station. The circle is we find out the distance is not enough for the Taiwan the wind front. The wind front the situation and the condition, especially for the traffic condition. So now the current satellite teams, we have a lot of the organization and the union and the university and etc. So we combine together to launch our first U-San ARS CubeSat. Now it's our giant behind us. It's our Dr. Liao and our president. Then you can find out we have the satellite communication webinar, and we have the automatic identification system for the network from the shore to the space. Now we can AIS information about the global resource. So this CubeSat with the AIS payload wants to monitoring the global resource and the global climate, especially the surface temperature. Now we have got another automatic packet reporting system for the land use. And with satellite mission nature in the principle of space efficiency as a BRNO. And now it's the 1U, 2U, and 1.5U and 3U CubeSat original. Now it's our block diagram, and we have the 1.5U CubeSat, the isometric the view and top view. And you see each components. We had the framing, the components, and the payload. This is our.
I think a little bit too technical. I would like to give some space to our other speakers because I'm really interested in, like, what is the role of the Czech researchers, and why, as Czech engineers, you're interested in building a maritime constellation? I would say there is not that much maritime traffic going about in the Czech Republic.
Of course.
Okay, thank you.
You're right. Ocean, so which is sort of tempting also, but there are other benefits of such system. For instance, as we know, the crisis that is happening right now with the Russian aggression, we know the satellites play a key role in helping the Ukrainians, and we can see, for instance, Starlinks are sort of solution that can reconnect again the troops or civilians. So this system also could potentially be used, for instance, for a restart from blackout, or information really downloading or updating from the remote, not only from the remote or distant locations, because Europe is quite connected. But in case of really failures, this could be used as a backup solution. So I think this system could be very interesting. And there is another technical aspect that I like. In fact, so far, many satellites are communicating only from orbit to Earth. But I think what could be interesting is to have connected satellites on the orbit, so internet on the orbit, which then would mean that I can really connect to satellite in real time. And to do that, I would really need some sort of constellation or formation of satellites and using some sort of technology. Theoretically, this could be possible with current technologies like Starlink, but they don't allow this. And also, we can use Inmarsat, but they are on a geostationary orbit, which is more difficult than, and so on.
Mm-hmm. How difficult it would be to build a constellation that could serve the Taiwanese needs and perhaps like the Central European needs in terms of designing the constellation?
So designing the constellation, it is all about preparation. I think the technology is there. So we will not need to develop any special equipment. But of course, the performance always depends on the quality of the equipment. So I think this is a key role of Czech industry that we can really add our knowledge and our experience to. There is also another aspect I would like to mention. Dr. Popela already presented our space application program, and I would like to greet my students which are in the back rows. But I think another aspect could be really some knowledge exchange, because as you mentioned at the beginning, we don't have oceans. So it means we don't have any experience with maritime science. And I think this could be sort of add-ons, because satellites are a really global thing. So I think this could be, there are really many aspects.
Mm-hmm. So where is the main kind of contribution, the sort of like main kind of strength of the Czech researchers when it comes to this project?
Mm-hmm. So in this project, it is telecommunications.
Mm-hmm. Perhaps Tomáš Koutník would like to add something. Where do you see your role?
Yeah, so for us as a small company, so we see basically two major regions where we can apply our technology, because as my colleague Martin Kubíček already says, we are all about the data analysis and optimization. So we can apply our technology in the initial stage, where there is still some pieces of other equipment, but there is still something to be developed. And also when the system is already operable, it will generate the data. And then our let's say part comes again. Then we can search for patterns in these data to recognize some specific aspects of what the traffic brings. Also, Xavier here mentioned also other topics where these satellites can be used for, and again, it will generate lots of data we can analyze. So we will assist in these aspects of the project.
Mm-hmm. How far are you in terms of implementation? When do you expect to see first hardware fly? What is happening right now at this moment, and what is the timeline of the project?
So for the moment, this program is on the first phase. So we already finished the CubeSat building. Now, of course, we have to redesign the architecture. And so this is a foresee that we have to work on that in 2023. And hopefully we can continue more feasibility studies and also on the timeline building. Because now we are getting all the partners, because for example, Thomas just said that the AI assisting approach will help us to develop the constructions, data analysis, and also afterwards application analysis. Our partner in Belgium, which is already a private company, they basically work on the at sea security and safety measures. They will certainly also inject their expertise on us. So they are already practicing on the maritime anti-terrorist attacks, maritime security measures. So we have to also integrate their program to our let's say, space tech applications program. So for the moment, the timeline is this year, since Taiwan also has heavily infected by the COVID, especially the border restrictions issue, we have continuing to have online meetings with all the partners. We just finished the phase of let's say, the discussion on the task distribution phase. So next year we are going to step on the concrete constellation, for example, the number of satellites we are going to build, and also collect the budget measures, and also to discuss how to share the burden, how to share the risk with all the partners. So that will basically a step like within 2 years, so until 2024. This is our plan for the moment.
Mm-hmm. Maybe let's ask our audience whether anybody has any question for you. We have about 5 minutes left, and if there are no questions, that I will ask some more, but I would like to give you some opportunity. Is there anybody who would like to ask our speakers anything? There is a hand. I think the microphone is coming.
Hello. So my question is this going to be an effort focused completely on the maritime traffic around Taiwan, or is this going to be also used around the Earth for other maritime traffic? And if it's only focused on Taiwan, are you considering an orbit that would mostly be above Taiwan, or essentially international?
Well, this satellite program, basically, as I said, is supported by Taiwanese public funding at the first phase. So, of course, the main target is to serve for the Taiwanese port security and safety, and also environmental observation purposes. However, we know that Taiwan is a very small market. So once this market is satisfied, the idea is not to become SpaceX or become Starlink, but we want to be part of the global supply chain with our own niche, like I think Professor Oltan also said, with the Czech Republic's niche, to have a place in the global sat tech application on maritime market. So this is the idea. And technically, I'm not the expert because I'm a political science background. So as I understand that, now there's a new telecommunication system which is developing in many different regions in the world. We call that the VDES, so the VHF data exchange system. That will basically complete the entire architecture of telecommunication to assist, to improve the harbor security and safety issue. This is our program is basically a part of that entire architecture building. For sure that we try to use Taiwanese indigenous system as a prototype for our own first, and then try to either work with the other competitors or become a part of the different regional supply chains. So this is basically our strategy behind the entire program.
Mm-hmm. Any other question? Thank you. There's another hand.
So I've noticed that you were using for your communication purposes, you were using UHF band or VHF band. I wanted to ask whether you took into consideration any other frequency bands, because nowadays, due to quite big overpopulation in lower bands, is there any sort of consideration maybe moving up to higher frequency bands, maybe X band or higher?
In general, this first launch will be more or less ham radio experiment. But later on, the traffic is not really huge. So with higher frequencies, there are more problems, such as pointing and other things. So this really depends on the data. This first constellation serves as some kind of test vessel, whether this technology is possible, whether it is achievable. But this really depends on the traffic. Of course, we can maybe consider S-band or X-band or maybe something higher, but there are higher costs and more problems with that.
Okay,
thank you. Any more questions? There is one hand.
Well, my question is related. There is a lot of activities in VLF, very low frequency band, which is able to penetrate, for example, deep into the ocean, and it's being used by submarines. This channel, very low frequency. So I was wondering if you have considered going that way also. And there is a usual advantage of the D layer that formed during the daytime, as opposed during the nighttime, the D layer is disappearing and people are using reflection of the D layer.
So I think so far these lower frequencies are not really the subject of the project, but I agree the lower frequencies have several benefits. As you already mentioned, we can a bit penetrate underwater, so we can, it depends on frequency obviously, but with lower frequencies there is a lower data rate. So this really depends. We are also in negotiation of some underwater communication, and this was one of another aspects that is not related to satellites, but we are working on underwater laser communication, which should serve to very high data rates, but it is still ongoing process. Yeah.
So you're saying it would be a combination of submarines and satellites, do I understand it correctly?
I think not.
Would you like to elaborate?
Well, I think, you know, as you, or as an expert immediately noticed, this is a possibility. Of course, this is a possibility. But we are talking about, at the current phase, this is a feasibility issue and also the cost issue. So indeed, the IMARC, so Intelligent Maritime Research Center, has already developed certain number of projects that, of course, work closely with Taiwanese Navy. However, you know, how far this project is, I'm not at the place to tell you more about that. But theoretically, technically, as we know, this is not a new technology we are applying. All that has been developed until now. So those technologies are basically useful and basically feasible. The question is whether it's worth for us to spend more money or much more effort to develop that. But we keep that in mind. So this is totally inside our consideration.
Thank you very much. That's about as much time as we have. So thank you all for joining us today, and thank you all for your great questions. Thank you. Thank you. So at the beginning of today's program, we heard from Jennifer Ngowan about the astronaut selection process. And whether the Czech reserve astronaut Aleš Svoboda ever makes it to space is probably still a question, but if he does, he may use some of the technology developed by our next set of speakers. So our next set of speakers all work on technologies for human spaceflight. They are designing future Mars station concepts, conducting studies for the planned station in the orbit around the Moon, and developing devices for monitoring astronauts' stress levels. Our first guest is René Václavíček, who is an Austrian space architect responsible for the early design of the iHub. The iHub, or the International Habitation Module, will be a key part of the Lunar Gateway, the space station that NASA and its international partners want to put into the orbit around the Moon within 5 years. So that's quite exciting. Thank you for joining us. Our second speaker is Vratislav Šálený of Brno University of Technology, who has worked on several space habitat concepts. So hopefully we'll learn a little bit more about the hopes of the Czech researchers to, take part perhaps in the Lunar Gateway or something. Thank you for joining us. And last but not least, we have Julie Dobrovolná, who is a researcher in environmental physiology and adaptation at Masaryk University in Brno and the managing director of Entrant, a startup company which is developing innovative techniques for measuring stress levels in astronauts. So thank you for joining us. Let's start with René, because you led the early study of iHub, and that's quite a big deal, because that's something that's really happening. It's supposed to launch in 2027, so that's really around the corner. So could you tell us a little bit more about it? What have you done, and what's going on with the project?
Yeah, for us it's indeed a big deal, because it's now the first piece of hardware we are involved in that will actually fly. And a few words, you may probably know that the space station will be a follow-up project realized by most of the partners who are also involved in the International Space Station project, namely the ESA of Europe, NASA of the US, JAXA of Japan, and the Canadian Space Agency. It will be much smaller, and it will orbit the Moon in a very eccentric orbit with altitudes varying from 1,500 kilometers up to 70,000 kilometers. And the orbit will be perpendicular to the equatorial plane, so there will be the space station will be in constant connection with ground control. And Europe's part is, amongst other parts, the provision of the what's called the International Habitation Module, and we have the luck to be involved in that.
So how far is this work? When do you perhaps see first mock-ups, first hardware?
Yes, we're at the moment we are headed towards the critical design review, which shall take place in the coming summer, and now we are starting to fabricate a one-to-one mock-up for the human-in-the-loop tests shall take place next year.
Thank you. Let's go to Vratislav. Vratislav, are there any ambitions for Czech researchers to get involved with such projects? And if so, where would you see your kind of niche in there?
Yeah, can you hear me? Ambitions. Yeah, I will start how we met with René, and maybe this ambition will come. We, let's say, met on the project which was called Deployable Habitat for Extreme Environments. it was made up under leadership of International University in Strasbourg. And let's say in that time it was paid by European Commission because for ESA it was really too much visionary project, yeah. But what is nice that now companies that let's say make the she habitat together with us, yeah, now are able and are allowed to design something on Lunar Gateway, European iHub, yeah. So it is really great. So from this you can feel the opportunity, yeah. So my suggestion are you have to recognize the opportunity early, yeah. If you recognize the opportunity, you have to catch the opportunity, then to build your heritage in space, know-how, let's say, in space it is a heritage, and to maintain the heritage, yeah. And all together you have to do in international team, yeah. We were a really international team. I think 4 or 5, let's say, companies around Europe, and now the companies are able to do real work on Lunar Gateway. So it's a really nice, let's say, story.
Mm-hmm.
Yeah.
Well, I understand that projects of this significance that will ultimately be built by someone like Airbus or Thales Alenia Space. So these smaller kind of players, how do they get in? Either René or Bratislav, who would like to answer? Both of you.
Maybe you can start if you like.
I would say even the big players don't play alone. And there's always space and room for SMEs and small companies like ours. It's also promoted by the space agencies. They have great interest to fertilize the whole scene. So I would say, as Radislav indicated, although there are some really huge players, the family is still pretty small, and we know each other, and also none of the projects we did in the past, and we did quite some, we did alone. We always were part of consortia, international consortia, multidisciplinary consortia with players of all sizes.
So become good at what you do, and there will be room for you in the bigger...
Make yourself friends, make yourself a name, and stay in touch.
Mm-hmm. Julia, your work is a little bit different. You're developing a technology that could monitor stress levels. Can you tell us a little bit about that and what role you foresee for that technology in human spaceflight?
Yes, thank you. As I was listening to René, to Bratia, and also to the precedent speakers, I was thinking, who am I to represent here? So now I just came to conclusion that I represent like the high-risk innovation, high-risk innovative research, non-incremental research. So I very much liked the debate on the failure and its role. Speaking about the technology we are developing, it's a unique technology that's based on thermodynamics, and its actual goal is to enumerate the adaptation cost of an individual or possibly some populations in the future in given conditions.
So what is it that you measure in the people?
Yeah, that's the question. Actually, that's part of the IP. So I'm not quite sure that I just can go into much detail, but definitely we're focusing on what is happening on the interface between the internal environment of the body and the external environment. I mean, we're measuring the temperatures and gas exchange, I would say. Yeah.
Mm. When it comes to astronauts' stress levels, I would say that it's kind of like accepted that if you go into spaceflight, it's a very high-risk business. You just accept it. What can you do to reduce astronauts' stress levels? They're in situations like, something suddenly happens and there is a disaster, what can you do to help them?
Well, that's
apart from selecting the most resilient ones.
I see. That's actually the very crucial question that goes very long time back into the 70s, when Hans Selye, like the father of the stress theory, introduced the concept of eustress and distress, saying in media, because he was very active in media, that it's good to fight stress, and that's the idea that it's good to fight the stress. In my opinion, the basic logic of the stress theory from the beginning was that it's good to have the stress reaction. It's inherently associated with performance, and we definitely want the astronauts to perform. So the goal is not primarily to mitigate the stress reaction, because it would definitely hamper the performance, but it's rather to somehow estimate the safety time before something happens, like a health outcome or possibly a deterioration in the performance. So we are not conquering the stress. I don't think it will be useful. We are very much looking into how long you can stay in certain set of conditions, environmental conditions, before it's bad for you.
Mm-hmm. So you assume, let's say it's a long-term mission somewhere on the moon or Mars, and you say, oh, this guy is reaching the brink, get him home.
Yeah, for example, this guy is reaching the brink, he cannot go for the EVA mission, for example, or something like that.
Mm-hmm. Yeah. So they would wear some sort of wearable devices?
Yes. Or maybe we can, because the variables that we use for the calculation are pretty generic. It's not anything special. The special thing is the algorithm, and not the variables. So it can be easily obtainable variables from the spacesuit, for example, that we can use for the calculation.
Maybe back to René or Bratislav. When you're designing this space station, do you think about, do you consider the stress levels, and are there any ways how to mitigate stress levels by the way you do things?
Well, I can say we have a lot of ideas, but when it comes to a real project like the IHAP now, we learn that there is almost no room for any countermeasure. You have to imagine you live in 8 cubic meters. That's about the habitable space of the International Habitation Module, and this place you have to share with 3 others. So that's, in other words, that would be a room 2 by 2 by 2 meters, and then you're locked in there for. There are other rooms, but they are not bigger, and there are not many of them, and you're locked in together with 3 other guys you don't even have to like necessarily, maybe, and that can be stressful, I would say. Yeah? And then, of course, first question, what can you do about it? Yeah? There's always the first question we're confronted with is, where's the window? Because we know on the International Space Station, the most popular place where astronauts spend every free minute is the window, but there is also the technical aspect of it. You can maybe implement something like a generous cupola in a low Earth orbit, but the moon is 1,000 times further away, and each window is a disturbance in the continuity of the structure. Glass is very heavy, so this is the first thing that's cancelled. Mm-hmm. Then there's other things that must be considered, like the noise level. You're living in a machine room. Most of the volume is consumed by life support systems. They make noise, a lot of fans. The only the only getaway you have is your 2 or 1.5 cubic meters of private space where you can close the door, and there are requirements of how to damp the noise in there. So there are different elements and different things to consider to keep the stress level acceptable.
Mm-hmm. So there will be no window in the moon station?
There will be, but not in the habitation module.
Mm-hmm. Bratislav, anything you would like to add?
I think René is now much more experienced with the design of the actual stuff on this module. Yeah. But of course, in confined space, it's a reason for stress, which is not, let's say, a positive for astronauts. It's clear, and it must be trained people that you have to understand that they will work in these conditions. Yeah.
Mm-hmm. So how does your technology come into it?
Well, I'm just thinking about how to put it a bit. Definitely, the technology we are working on at this point is capable of detecting metabolic changes, or I would say intensity of metabolism in the person. So what we can see if the person is not performing very strenuous physical activity, that something is happening. The interpretation of the results that we already have is a bit complicated by the concept of stress and of its, I would say, adversity, because I really don't think that it's good to have no stress or to try to achieve it. Of course, if we talk about these isolated confined places, it's something completely different. These people are extremely limited in their movement, limited in their social interactions, so it's a different situation. What we could offer is the calculation of some safety time between you have to move, for example, into a private part of the area, for example. So that's what comes to my mind at this point. But we are now just making the algorithm stronger and everything. So just not at the TRL level, I would say, to implement it into the habitat.
Let's see whether we have any questions in the audience. Anybody would like to ask about? There's a hand in the back. Do we have the microphone anywhere? Or you can just shout at us.
Can you tell me, please, the basic external dimensions? I would like to compare the inner dimensions. You told it's 2 by 2 by 2. What's the external ones?
No, I was just comparing. Yeah, speaking of the dimensions, we started off in the first phase with a cylinder similar in its dimensions, similar to what we know from the ISS. Speaking of more than 4.5 meters in diameter, if I'm not mistaken, and about 6 meter length. And then during the project, it turned out that maybe the SLS won't be finished in time, so we had to fly with the Falcon 9, and so the whole module had to shrink. Meanwhile, we know that we can use the SLS, but due to mass restrictions, we kept the size, so we shrank it down to 3 meters outer dimensions, diameter. But most of the interior volume, as I said before, is consumed by machinery and subsystems. And what makes it even worse is that everything has to be redundant. So every piece of hardware inside the module has to be, you need to build it in twice. So that consumes a lot of volume. And what's actually left at the end is just a corridor. You have you have to imagine you have a cylinder with a hedge on each end and 2 hedges on the sides, and there is a corridor going through the length axis, crossing with another corridor, and that's about it. So even if you want to pass one another, it's already, you have to interrupt whatever you're doing at the moment to let the other fellow pass by you.
Any other questions? There is a hand over there.
Sorry, to be even more precise, to compare it on the International Space Station, where you have had the larger diameter, you had an interior cross-section of free space of 220 by 220. So that would allow you to even stand upright, given there was gravity. But now you have a cross-section of 120 by 120. So that changes the whole orientation inside if you want to stretch out, you have to turn 90 degrees.
So I was wondering if there were any studies or considerations on what is the effect of, for example, hydroponics or things reminding astronauts of home, like growing plants, on the stress level of the astronauts, and if it was considered putting more of these things into the spacecraft to help them.
If I may ask, and thank you for the question. We don't have solid numbers on that, but what I can tell you is there was another project we did a couple of years ago together with the DLR in the German Aerospace Institute. We built a greenhouse in two 20-foot containers and shipped them into the Antarctic to the Neumeier, the German Antarctic station. And it was set up to run for 1 year. There to provide fresh vegetables to the crew there. And it was so well received that they kept it for another 2 years. And it provided them, and they said until they got it, they didn't realize what they actually missed the most, to bite into some fresh green stuff which they don't have for half a year during the winter time.
May I will probably add a bit. Inherently, the stress levels are associated with the stimulation of our senses, and not only like one by one, but by the multisensory experience that we have of the surrounding environment. So more diverse the multisensory experience of the environment is, the more resilient the person is to, for example, tackle the confinement or isolation and everything. So to focus on the sensory quality of food, of the smell of food, for example, of touch, of the, I would say, underestimated senses sometimes, in my opinion, represents a very interesting gap of knowledge, where to go, where to focus to improve the well-being of the astronauts. So definitely I would say yes, even though I don't know the exact data too.
And in our recent designs, we integrate the greenhouse into the habitation space as an integral part of it.
So there will be room for a greenhouse in the Lunar Gateway?
Not in the Lunar Gateway, but maybe in one of the future projects which are sort of in the pipeline.
Any more questions? There is a hand over there. Microphone is coming.
Thank you. I would like to use the special kind of expertise gathered here, and it's about inflatables, because I know Dr. Shalini was working on it in the past and cross-check the knowledge with the other two. It's about the beam module, the expandable module currently on ISS. So I was wondering whether there are some maybe lessons learned from that could possibly be applied in cislunar environment, or maybe it's the radiation that just forbids this right away, or whether you maybe you didn't even consider it because it was not part of requirements for the gateway, but maybe with your expertise, like the combine of your three, I would be interested if you have anything to say about it. Thank you.
Maybe. I think inflatables are, let's say, a quite common structure like another think wall structure, but the advantage is you can, let's say, pact and employ or deploy the space. Yeah, so it's a very promising concept, but of course you are not able to use traditional materials as is common for a long time. You have to use armored Kevlar and so on, and you have also to find a way how to place the special layers which let's say save the life of the crew in front of micrometeorites and so on. Yeah. But I see a large potential for inflatable structures. Maybe you will tell.
Yeah, I agree. I mean, in terms of radiation shielding, inflatables are not worse than any other architecture. They are not worse than aluminium vessels. And when it comes to planetary architecture, we anyway need to find other strategies of radiation shielding. We are in our work, we are heavily involved and very much interested in using local material, regolith, as a feedstock for 3D printing in order to build up radiation shielding structures. And inflatables, at least in our concepts, inflatable structures are always part of it, because in the end you need something to hold the air together, and inflatables are promising technologies for the reason Vratislav mentioned.
Yeah, so inflatable structure could be also the thin membrane, which make the clean room inside, and outside there are, let's say, layers of regolith. Yeah, it's also a possible concept. Yeah.
Well, maybe I would just add very generally that, because our perception of space, of the, I would say, indoor environment, heavily shapes how we feel, of course, and I would just probably expect that the development of these inflatable designs would make it possible to provide specific design adjustments that can be, if possible, if feasible, due to the space restrictions, of course, somehow used to mitigate the stress reaction of the person, or possibly several persons in the area. Yeah.
Thank you very much. Is there anything anybody would like to add? We have just like 1 minute left, so any concluding remarks? Anybody?
Yeah. Maybe my remark, because now we started with the stress resilience. Yeah, we have already small project from ESA, but we let's say it is aimed for terrestrial use for firefighters. And there are people that are extremely, let's say, stressed by hot and also psychic, let's say, work. And I think we could use later on the technology also for all of us, because as you can see the extremes here on the planet, we are in extreme, sometimes in extreme hot, and maybe it will be worse, so the knowledge will be useful for all of us, I think.
So Julia,
thank you very much. I just wanted to add to Vráťa, because I completely agree that there is a huge translation potential from the extraterrestrial use to the extreme environments, and not only extreme, but terrestrial, generally terrestrial environments. I just wanted to emphasize a bit the topic of human health and space, because there were so many presentations on technical aspects of various life sciences, engineering aspects of the space research. But there's also the possibility to investigate how the human body behaves, and that's what we're doing, and we're happy to do that, and I hope that will continue successfully. Thank you.
So thank you all for being here. It was a really interesting conversation. Thank you all for asking questions, and we will now move to the final segment of our program. Our final guest is known for making beautiful photographs of solar eclipses. You unfortunately don't see them behind me. I was hoping we will get to see some of those photographs. But anyway, these images are not just beautiful, they also have quite a unique scientific value. And I think I will leave it to our final guest to explain why. Our next guest is Professor Miloslav Drukmiller, who, apart from being known for making beautiful images of solar eclipses, is also the head of the Institute of Mathematics at the Faculty of Mechanical Engineering at Brno University of Technology. Hello, and thank you for joining us today. We should also be joined online by Sharia Habal, yes we are, who is a solar physicist and astronomer at the University of Hawaii and a frequent collaborator of Professor Drukmiller. Hello, Shadia, do you hear us?
Yes.
Fantastic.
Thank you.
So let's start with the first question. Professor, I can't help but ask, Doing solar research using solar eclipses, that sounds to me like an awfully inefficient way of doing things, because you only have a solar eclipse like once every 2 years. It only lasts like 2 minutes. You have to travel all over the world, while we have all these, spacecraft in orbit. We have the solar orbiter now, which is making really beautiful images. We have the SOHO spacecraft, the Space Solar Dynamics Observatory. So what is the advantage of doing what you're doing compared to those probes?
Yes, thank you for the question. So really it looks like a nonsense, but it is not. If you imagine these spacecrafts observing sun, sent to the Earth about 5 terabyte data per day. So to observe total solar eclipse, which lasts, as you mentioned, several minutes, looks like nonsense. But the problem is that there is in the solar spectrum one region which is extremely complicated for observing. And it is visible part of the spectrum. The reason is that the solar photosphere, it is the, let's say, visible surface of the sun, is about 10 million times more intense than the solar corona. So we need some occulter. And this occulter must hide the extremely bright solar photosphere. And this occulter must be very far away, because if you put the occulter very near to the telescope which is observing the sun, the image will be in the corona completely destroyed by diffraction. And that's the problem even of cosmic coronagraphs. So we need a huge occulter and very far away. And up to now, the moon is the only possibility.
Professor Haba, would you like to add something?
Yes, we actually prepared a few slides, if you will allow us to share them, and then I think it will make the point easier to convince people of the value of
Control of your presentation, I would assume, or perhaps
Okay.
our technical support could allow you to share.
No, I can.
Yes,
I can do it.
we see your slides.
Yeah. Okay, so this is actually, I would like to add that Miloš and I have been long-time collaborators since 2006, and it's been the question I think we ask ourselves: does an astronomer and a mathematician have in common? And as you will see, we have lots of things in common. In particular, our love for the research we're doing and the understanding of the corona. So I think in the following slides, Miloš and I would like to illustrate why what he said is so critical for understanding really the closest star to us and how it expands into interplanetary space and impact all the objects in the interplanetary medium. So as you said, you were asking, why should we wait for total solar eclipses? Well, as Miloš was explaining, and here this is more graphical, for example, you take an image from the Solar Dynamic Observatory. It is from multi-wavelength observations that Miloš had compiled together. And you can see that in the extreme ultraviolet, the advantage is you see the surface, you can see the corona projected against the surface of the sun, as well as some extension above the limb. Now, this is clearly not sufficient to understand how this plasma or gas expands into interplanetary space. So if you take a coronagraph like what Miloš was explaining, you have a terrible gap here. You don't know how things started, and you have this gas that's expanding away from the sun. So you put the two together, say you have both instruments working simultaneously, and you still have this critical gap. Now, these observations, the examples I'm showing are from coincide with a total solar eclipse in 2013. And if I combine them together, you can see the incredible details that all these instruments at present are missing, and that you get from this very short observing opportunity. And you can see here in this particular example that there were these two bubbles that are expanding from the corona that you would have never guessed existed had you been looking at just this. So this is why the eclipse observations are so important, because they're exploring this part of space that at the moment is excluded from any access by any existing observatories. Now, this is another example of the coronagraph, the white light coronagraph, and the corresponding white light image from the eclipse in 2015. So not only are we seeing all the details of the corona in this space here, but you can see that the spatial resolution of the eclipse images is far superior to what's existing at present. Now, grant you, SOHO was launched in 1995, so it's not, you know, it's not surprising that they didn't have the same technology, you know, the advancement in detector technology like we have now. So the tools that Miloš was describing are the white light and what we call the coronal emission lines. And I just want to explain very, very briefly in a simple way what we mean by this. So the corona is very, very hot. It's over 1 million degrees, whereas the surface of the sun is like 6,000. So the big puzzle is why, how can a gas suddenly start to increase in temperature above the surface of the star? So one really extremely powerful way of exploring how this temperature rises and how the distribution of the temperature in the corona varies is to look at light or emission from different ions in the corona. And it just so happens that iron, the element iron, has a sequence of ionization states that allow us to pinpoint different temperatures in a very precise manner. So this is an example of what we call ionization fraction versus electron temperature of these lines. And just I highlighted two, which is the iron 10 plus, which is what we call iron 11 here, and the iron 13 plus, which we call iron 14. You know, the astronomers use Roman numerals, the particle physicists use the ionization state. So you can see that the two peaks here are distinct. So if you see something in iron 11 and you don't see it in iron 14, you know that the temperature, what the temperature is. And this is what we're show in this example. So these observations were taken in 2019. We had different filters. And if I didn't tell you that this was the same eclipse, you probably wouldn't have guessed. Because look, each one of them looks so different. So here, so each image here is representing a different temperature plasma. So for example, this one is around, you know, 1 million degrees. This is 1.2, even though the temperatures are close, but you can see that the corona looks very different. And here we're going to 1.6 and then 1.8. And again, the corona looks very different. So these tools are extremely sensitive and probe, you know, the distribution of the electron temperature in the corona. This is just a comparison of these with color coding, just to show you how the different temperatures map different regions of the corona. So everything that's kind of open and expanding into space is better seen in iron 11 or iron 10, and the rest that's kind of confined to the sun, which is much hotter, is best observed in iron 14. And in addition, you will see also evidence for some turbulent structures, which are very surprising, and they only appeared in the eclipse images. People hadn't seen them before. This is a comparison for the same eclipse of the white light, which is comparable to what the eye sees, and also the composite from the filters. And this outlines this turbulent region. So if we just limit ourselves to the white light, we have no way of telling what, you know, is it all at the same temperature or is the temperature very different? And sure enough, as I showed earlier, there is a distribution of temperatures. So although we say the corona is hot, well, it's not uniformly hot. And the big question is what makes certain regions, certain magnetic structures get to much higher temperatures than others. So what, yes.
Do you hope that these solar eclipse observations could solve the mystery of the heating of the solar corona? Because that's one of the big questions in solar physics, right?
Yes, so I think we're approaching it in a remarkable manner with these, because once we know that not everything is at the same temperature, then it's to explore physical processes, you have to run some models. And so what you put in the models gives you an outcome, which you then compare with the eclipse observations. And so you iterate between the two to kind of constrain your assumptions, your starting initial conditions, to improve on the outcome from the model calculations. So we know about certain physical processes, such as the existence of waves associated with magnetized plasmas that can heat the plasmas in different manners. Well, we know about a process called magnetic reconnection, whereby the magnetic field lines interact with each other and locally heat the plasma as well. So by exploring these different processes in the models and then comparing the output to the eclipse observations, we can really get a much better assessment of what the processes are.
Thank you for now. My next question is about space weather, because that's another big topic that we hear about a lot currently. So that will be for Professor Druckmiller. Maybe space weather, many countries see space weather as a big risk, similar to a pandemic. It could disrupt satellites, power grids. Do you think your research, your photographs of solar eclipses could contribute in any way to help us better predict space weather?
Definitely, yes. Of course, we are very far from being able to predict the risk of, for example, this coronal mass ejection. But of course, we are able to put in the mosaic of the knowledge of solar corona some very important items. Especially our research was very successful in finding the area of the corona which is occupied by collision plasma and where is the border between collision and collisionless plasma. It is very, very important for the solar research, because if you, for example, would like to observe these different iron ions and to distinguish between different temperatures, it is possible to make it not only directly very near to the sun, but after some distance, which is very near to the sun, it is the fraction of solar diameter, the ionization state freezes. So it means the plasma is collisionless, and the iron ions have no chance to reconnect again with electrons, and that is why we are able to compare our observing, for example, with observing of satellites, which are measuring the ionization state of ions very far from the sun. So I think that from that point of view, our research was very important.
Professor Hubble, would you like to add anything to this?
Yes, so I'd like to just provide the evidence that Professor Druckmiller was mentioning. So what we did from our collaboration starting from 2006 until now, well, we missed the 2020 and 2021 eclipses because of poor weather. But so this compilation shows from 2006 to 2019, when we had both white light, which are shown in the left panels here, and the combination of iron 11 and iron 14 straddling over a solar cycle. So one can see that the shape of the corona changes, the distribution of the temperature changes, but what is evident is that the field lines that seem to be streaming away from the sun are everywhere, not just limited to the polar regions. And then the dominant ion that we see along the open field lines is what we call this iron 11 line, or the ion which is iron 10 plus. So, for example, taking this image here, we know that for everything that's streaming away from the sun is this iron 10 plus. And then we compared our results to what was observed in interplanetary space. So there are instruments that capture, the different charge states of iron. And what we found is that although they observe a whole range of charge states, there seems to be a band around the iron 10 plus in interplanetary space that really stays there. It's just, no matter how the speed of the solar wind varies, the charge states are very almost constant. So this is the first time we were able to make a connection between what the origin of these, the iron 10 plus to the sun.
Thank you.
Yeah.
How did you actually find that you can make this type of research during solar eclipses?
It was just a rather complicated story because I was interested in solar eclipses as a mathematician because my main subject is image processing. And to obtain images you saw there is a rather complicated task. You need several hundred of images and rather complicated calibration and some mathematical tools to visualize the structures. And by chance we find the possibility to show the images at the internet, etc. And by some complicated story, we find together Shadia and me and start very fantastic cooperation, which is lasting for more 15 years. And from the very beginning, for me, there was definitely no idea about science. From the very beginning, it was the mathematical task to create some image. But when I started the cooperation with Shadia, it was possible to take full advantage of these images. And finally, Shadia and his team were able, her team was able to give us, let's say, tasks, what is interesting and what to do. And it is a rather unique cooperation between Institute of Astronomy and Institute of Mathematics. Mm-hmm. Yes, and so I think that is why the results are so interesting.
Mm-hmm. How much data can you get from a single eclipse, and is it enough to gather data at these frequencies that the total eclipses happen?
Yes, it is a very interesting question. Of course, the eclipses are seldom, so we need more eclipses, but it is not possible. It is the problem of the nature. But every eclipse is for us about 2 terabytes of data, and the processing is really a very hard task. So if we have enough data, yes. From the point of the processing, I have more than enough data. From the scientific point of view, it will be better than every new moon will be a total solar eclipse. But unfortunately, the orbit of the moon is inclinated to the ecliptics, and that is why so solar eclipses are so seldom.
Thank you. Are there any questions in the audience? There's a hand.
Thank you for this interesting presentation. Maybe this is a question that can be answered in the evening session. But knowing the spectrum of iron, which is really dense in lines, you really care about some interferences in your wavelength spectrum, or you just really sure that those are distinct lines, with no overlap of other ions, other elements, and so on?
The big advantage of visible part of the spectrum is that there are only several iron lines of different ionization states, and they are separated. So we are able to observe one ion, and we are absolutely sure what we are observing. For example, if you compare it with images which are able to obtain a solar dynamics observatory, which is observing the sun in extreme ultraviolet part of the spectrum, it is not possible to separate these lines because in the wavelength range, which is observed in one channel, there are many lines of different elements, mainly irons, and they are not separated. And the spectrum is highly dependent on the stage of the corona. So in the active region, it is different than in, let's say, the completely quiet corona. So if, for example, you see an image which is said to be iron 14 from SDO, it is not iron 13. It is an image which is probably dominated by iron 14. But in the visible part of the spectrum, the spectral lines, we are able to separate, and that is why we have perfect information about the electron temperature.
There is another hand.
Question related to the amount of the data you mentioned. You mentioned terabytes, but in high energy physics, it's nothing basically. Yeah. And that's why I wanted to ask you, why is it a problem for you? Are you using some grid for, working with the data, or are you running on some machine and this is a problem? And related question to which you don't have to answer now because it's maybe wrong or too technical is, I can imagine that you are interested also in time development. So the processes which my colleague mentioned, you have as your colleague mentioned, you have a physics picture modeling for this. So if you look on the time development, you know what you expected in the next, let's say, 10 minutes or something like this. So you can confirm, you take time slice and then you can compare with after 10 minutes and to see if your model is really working or not. But coming back to the amount of the data, so what is the problem there with this amount of, with these terabytes, please?
I think there is no problem in it because we need, let's say, hundreds of images taken with different filters, and let's say 10 times or 20 times as much calibration data. So the problem of the amount do not exist. Definitely not doesn't exist. Yes, it is easy. Another problem is, you mentioned, if it is possible to see some development in the solar corona. It is tough because the total solar eclipse is visible in the typically very narrow band of totality, and it lasts hours, but you need different observing places for obtaining images with time difference of minutes or even, let's say, hours. And it is not easy to achieve, or typically it is not possible to achieve, yes?
Sorry if I interrupted, but for this you can use, this broader window out of this, and you can study your processes during a normal situation, really filtering out of the sun and really concentrating. And then for the area where you are in which you are really interested. So you can train in fashion language, train your models on outside, right, to achieve, there you can get infinite amount of time. Okay.
Yes, about modeling, I will speak in the lecture, which will be in the evening, but the problem is very complicated, and we are very far from the stage you explained to, let's say, be possible to model exactly what will be the development in the solar corona.
I will wait. Thank you very much.
It is very complicated task.
There is another hand up there.
I would like to ask about the filters. Could you provide us some information about the design process and manufacturing process about the filters that can see the spectral lines?
The problem is rather complicated because not only one filter is necessary. If you take into the consideration the spectrum of solar corona, so more than 99.2% of the light is the scattered light on free electrons, which is coming from the solar photosphere, which is hidden by the moon. So we must remove at first nearly all this continuum to obtain the image of the line. So that is why we need one filter just exactly on the spectral line we would like to observe. And the second filter has the wavelengths shifted of several angst nanometers far from the line. And then we must subtract these two images and, let's say, take into the consideration the difference between the intensity of the continuum between these two wavelengths. And after this subtraction, we are able to observe the line. And the transmission of this filter is typically 5 angstroms. Yes, and these filters are manufactured. Up to now, we are using the filters made by Andover company.
We have time for one more question. Anybody?
Yeah, I have remembered the book of Richard Feynman, You Can't Think It Seriously, Mr. Professor, or something like that. And there is written on the backside of the book, after I'm going to die, I will ask God 2 questions, why, and maybe quantum mechanics, and second, why turbulence, yeah? And you said that on the surface of sun is also turbulence. And the turbulence is something for me, what I know from fluid mechanics. It's the same turbulence on close to surface on sun.
The problem is that near the surface of the sun is vacuum. What we say, this surface of the sun is in reality no surface. It has nothing to do with solid surface. It is the layer which is not transparent. So the interior of the sun is not transparent, and then we come to the layer which is more and more transparent, and then we reach the, let's say, mathematically defined surface. It is not really surface, from which the majority of radiation is coming to the space, and it is called photosphere. And the density of the photosphere is comparable with the density of Earth's atmosphere in the altitude about 60 kilometers. So what we see is very thin gas, and if you go further and further from the sun, we are in the perfect vacuum. And as I explained earlier, if we reach the distance of several fractions of solar radii, we reach the idea where the plasma is collisionless. Yes, and so that is why the turbulence has different properties than we are used in, let's say, gas of the density of, let's say, air at Earth's atmosphere, in Earth's atmosphere. Yes, so it is mainly interaction with the gas which is ionized and magnetic field of the sun.
Yeah. So something chaotic but not directly turbulence.
Yes.
Yeah,
Yes,
okay.
yes.
So thank you.
Thank you very much. Thank you all for your questions. Thank you, Professor Druckmüller. Thank you, Professor Habal. This is about as much time as we have for this session. Thank you for being here with us.
Yes.
Thank you.
And we are nearly at the end of the official part of our program. I would now like to invite Jiří Hlinka, the Dean of the Faculty of Mechanical Engineering at Brno University of Technology, who will present the closing remarks. Oh,
Ladies and gentlemen, I was asked for closing remarks of the event, but from what I have seen today and heard today, I can say and I believe that in space research we are still on the beginning. We could see and hear comprehensive information on space activities from different perspectives. From universities, we could see activities dedicated to development of highly sophisticated equipment, but also activities focused on basic research of fundamental stones of the universe, or research of limits of humans in space. Today, you could see a lot of enthusiasm, will to move boundaries of the knowledge, and willingness to invest an impressive effort in it. However, In addition to be able to move those limits in space research, we need to invest also in education of young generation, of young scientists. This remark goes to all representatives of the government, local authorities, and European institutions. I understand that we have an enormous number of problems down on Earth, but please do not resign and look to the future. Let me use this opportunity to thank to all participating colleagues, not only those of Brno University of Technology, but also colleagues from other universities, business companies, and institutions. You have shown today an impressive background in airspace. Congratulations. But I would also like to thank organizers of this event for the organization and for the effort put in this event. And special thank goes to Teresa Pulharova, who is the guide of today and who made the impressive work done in guiding us today. So thank you, Teresa, and please clap your hands. By the way, this event is not finishing. You will have opportunity later in the event to see accompanying lectures. I was just informed that those lectures may be a bit later, like 7:45 or something like that. But you will have opportunity to see an additional information about space and a lot of information that is related. And as far as I know, for example, Professor Druckmiller, I know that you will receive a lot of facts, but you will have a lot of fun as well. So you are invited, and please enjoy this evening.
Thank you. Thank you very much. So yeah, this is the end of the official part of our program, and at 8 p.m. I believe the unofficial part of the program will start. As Mr. Linka said, there will be another lecture from Professor Druckmiller. We should also have another foreign guest, if I'm not mistaken, Professor Klaus Schilling, who is one of the pioneers of CubeSat technology, and he also worked on some really famous European space missions, such as the Comet Chaser, Rosetta. I'm not sure about which one he's going to talk. And we will also have a screening of a comedy called Mars, which was shot at the Mars Desert Research Station and features an experimental habitat developed here at Brno University of Technology. Thank you all very much.